Hello, everybody. Good morning, good afternoon, good evening, wherever you are. We have quite an international audience today. Happy to welcome you to the second meetup of the Swiss chapter of the global token engineering community. Thanks a lot for joining today. Please note that this online meetup is recorded. My name is Moritz Kaminski, and together with Jonathan Gabler, we are running the Swiss chapter of the Global Token Engineering community. After our launch event in February, where we introduced basically the practice of token engineering as an emerging professional cryptoeconomic system design. In today's event, we will explore one of very interesting primitive, namely token bonding curves. Why we see bonding curves basically as a interesting role in shaping the token economics for a given crypto ecosystem. With many projects like games and also dApps spiking in popularity recently. Before becoming just a one-hit wonder, it is important for a project team to turn a positive launch into a long-term success, given the right incentives to also participants, and that they can use the reliability of a bonding curve to continue supporting communities and ecosystems and games beyond their first interaction. And to give you a good situational awareness about this building block, we managed to put together quite a great lineup today. And with this said, now I would like to hand over now to Jonathan, who will be the moderator of today's meeting and also guide you through the agenda now.
Sure, thanks, Moritz. Let me know if you can hear me well and see me. So it's great to see everybody. And I have a great news to announce. So this will be, if everybody shows up who registered, it will be the biggest token engineering meetup to date, which is quite exciting. And it really shows that token engineering is gaining traction. People are becoming aware of that there's an industry or a discipline forming that's here to stay and that takes building these systems very seriously. And I also think it really shows the great work that Angela, for example, and many other people have done in this community. I think many of us who are in this community can say that it's really a community where there's lots of people contributing very proactively, and now we're kind of seeing the fruits of all of this. So this is the second meetup that we're doing at TE Switzerland, and we're really trying to, at Token Engineering Switzerland, we're trying to carry the sort of the spirit of the global movement into Switzerland, because there's a large community here, but we think there's a bit of a vacuum when it comes to token engineering and the practice of token engineering. We also want to really create impactful events, and what that means is we really try and do events for the audience. We try and think about when will the audience go away from an event and say, I really learned something today. And what we try to do in this particular meetup is really to put together, as Moritz said, a lineup of different people that in aggregate, I think will provide a very nice sort of sophisticated situational awareness of what's up with bonding curves. There's really a lot of dynamic when it comes to bonding curves, especially in 2020. I don't know, some of you might have seen, I put together a bit of a timeline. It's very much not complete and not kind of meant authoritative, but really a kind of research, documenting my research. And you can really see there's lots of adoption just in recent months. There's lots of projects coming up following, I think, a lot of great thought leadership, and a lot of the people involved we have here in the call today. So I wanted to quickly and see if that works, share my screen and walk through the agenda. Please let me know in case that does not work. So I'm sharing my screen now. Okay, you should see my screen. So we're going to start off with a little bit of historical context with Simon. I think it's always helpful to understand the present and to understand where we are to understand where we came from. And I think Simon has been there from the very start, and will provide a great context and perspective on how this idea developed over time of how basically this, the process of knowledge making around the idea of token bonding curves evolved over time. Then we thought it would be good to kind of create a baseline for beginners, because not everybody in this call will be an expert, and we wanted to create an opportunity for people who are not experts but beginners to still jump in and understand the rest of the event better through this introduction. And then we have a sort of a battery with 3 case studies and 3 design archetypes. Molecule and Paul you'll handle both in one session. And afterwards, we split the design archetype, the token bonding curve design archetype talks from their application, because we thought that might kind of be beneficial to people to develop an understanding of which kind of patterns of token designs fit to specific use cases, and maybe that kind of sparks thoughts for for future application. And then at the end, we're going to round it off with a perspective from Dr. Michael Zargham, who's going to speak about how scientific research looks at token bonding curves. Because one thing, and I've been looking a bit into the history of research recently, what you see is that there's really different perspectives on a specific subject, and scientific research looks at a thing that we call token bonding curves really as an epistemic object, and tries to understand the patterns and tries to abstract and really tries to understand the underlying structure of that epistemic object. And I think it kind of complements the very implementation focused sessions before very, very nicely. So this is what we've planned. I hope you're as excited as we are. So let's get started. One other thing, this is Token Engineering Switzerland. The Swiss, they're quite obsessed with time. So we want to be culturally sensitive. We're going to try and run it as scheduled. We've asked the speakers to be on time. You can ask questions. You can ask questions by submitting them to me or to Moritz. And you see, if you go to the participants, you see a host in brackets. And if you submit your questions there, I'm going to ask them to the speakers after their sessions. We only have time for 1 or 2 questions per speaker. So this will be a bit of a compromise in this event because we have so much content. So try and ask questions which are as relevant as possible for everybody. And that increases the chances that they're going to be selected and answered. And with that, having said that, I think we should get started with the first speaker, which is Simon de la Rouviere. I do not think for many here he really needs an introduction because he's a very well-known figure in the space, but he's doing so much, and also having read a lot of your articles, Simon, it's quite impressive what you're pulling off there at various ends. You're a creator, you're an artist, you're a technologist, you co-designed the ERZ-20 standard, and many regard you as the inventor of token bonding curves, and we're very excited to have you today and look forward to your chat, to your talk.
Awesome. Thank you. I just need to enable screen sharing. Okay, let me do this. Okay, screen should be on. And yeah, that should be working fine. I assume it's perfect.
Yeah.
Cool. Okay. So for this kind of talk, I just wanted to give kind of a background to like what kind of steps led me to design bonding curves initially, at least from my perspective, and to showcase, steps of evolution that happened to bring it to where it is today, or at least when it was originally created. So when I look at something like this, sorry, I just want to move this bar, it's in my way. There we go. So the question I wanted to ask when I looked at blockchain technology in its earlier days is I saw this possibility for us to create technology and tools that can reduce the cost to organize through the automation of various protocols. And I use the word protocols here to indicate sort of technical protocols. It's like, how do we update information? And also social protocols, like how do we interact and what do we use to interact? So it showed immense promise in that capacity to allow us to coordinate globally in a new manner by having this sort of database that is collectively shared and updated in a simultaneous manner. And so under that umbrella of the reduction of costs, I also look at the economist Ronald Coase's theory of the firm, which talks about the reason why firms or organizations exist is because they reduce the transaction costs to coordinate around a shared goal. You know, we start an organization with the belief that we want to achieve something, and an organization work better than what exists in the open market because the people inside it don't have to incur specific kind of costs, whether it's like mental, resource costs, social costs, to achieve something. And that's why firms exist. This is at least Coase's theory to why firms exist, and everything is not just a completely open, free market. And I want to specifically look at one component, and this is how I got and how I proceeded when looking at the stuff is, and this actually comes from my master's research that I did. I wrote a thesis on information overload and how we process information in an online context. So I looked at the reduction of costs from basically two perspectives. It's specifically social transaction costs. Is we can reduce the cost to coordinate by essentially boosting positive communications, and on the other side, hindering negative communications. So one way to put it is, you know, when you have positive or novel communication, you do more with less. This is simple to understand. You know, it's not verbose or lengthy. That is, the word's incorrect. It should be negative comms, not comments. But the negative communication is when things happen where you say less with more. And the best example of this that we're all familiar with is spam, right? You want to reduce spam as communication in organization because it adds to the transaction cost to coordinate. And so from there, one of the things that there are different ways to achieve this, to like boost the good signals and hinder the negative signals. And one of the ways in which I looked at was simply to add some economic costs to communication. This is one form of sort of execution or implementation to achieving this goal. And a simple example of this is, you know, when bandwidth is low, you know, no one is talking or sharing valuable information, you kind of want to incentivize people to communicate. You know, when there's a vacuum of communication, it's like, we need something to happen, but the right people aren't talking to the right people or not sharing to the right channels. Literally either incentivize them to do so, or in a blockchain context was literally, can we just pay people to communicate when the bandwidth is low? On the other side, when the bandwidth is high, you know, when there's too much chatter happening, too much communication, too much noise, we kind of want to incur some kind of economic cost to communication, such that when we do communicate, it is a very high signal. So we switched it around to saying people pay to communicate when the bandwidth is high to reduce spam. There are another way that we are much more familiar with that reduces social transaction costs, and that is the concept of ownership or equity. And this we see in modern corporations and firms all over the world, and to another extent, we see ownership over platforms and networks with blockchain technology through tokens and cryptocurrencies. So the value of equity in reducing social transaction costs is that it allows you to increase leverage when you organize. So one way to think about it is, if I want to see something happen in the world, forming an organization with other people allows us to work together to make this happen. But the value of equity in this context is that it gives us an additional incentive or bonus, such that if we achieve our goals, we maximize the value that's being produced. We all share in the company and the goal that's being achieved. So equity increases organizing in novel contexts. So I use the term low bandwidth environments, which is essentially new industries. Like there's always this concept of like a gold rush when new technology is invented, when people are trying to use it to invent new things, and then investors put money in there, and like young engineers go there and try to figure things out. So equity, in some sense, is the execution of this idea where it tries to seek novelty. And on the other side of the spectrum, which is in high bandwidth environments, economic environments, where you have, for example, have an established industry, the existence of equity can sometimes like overly incentivize people that brings forth negative effects in the market, things like cartel behaviors, anti-competitive things, monopolies, oligopolies, and so forth. So it's largely these two concepts that I saw that was something that we could potentially use to allow us to coordinate in a new fashion across wherever you are in the world, and using blockchains to do so. And from those two concepts, I started thinking a lot about this and trying to figure out what are the sort of ideas out there that we can use that allows us to coordinate, but also create wealth together. And so I started writing a lot, talking to a lot of people, and sharing these ideas. In the beginning, there wasn't many people around that were as excited about these ideas, but there were at least a handful of people that I shared some of these ideas with, such as Maciej Opinski and Meher from Epicenter. And so we shared a bunch of these ideas around, and it took on different forums over time. And I wrote a bunch of this. I called it different things like hashtag markets, meme markets, attention markets, attention bonds, content producing DAOs. All these things try to work together to solve two problems. Reduce the cost to communicate, boost novel signals, but also at the end, like create value together. And a big portion of that was actually, and this is where some people might always find it strange, is like much of these ideas came from seeing Dogecoin succeed as as something that exists. It was a cryptocurrency that had no technical innovation. It innovated through what it represented. And that would seem incredibly powerful as an idea. Could we recreate Dogecoin for many different communities where the community can create wealth together while simultaneously communicating in a new manner? And so over time, I worked on these ideas. The hashtag markets, for example, was very close to what the bonding curve was, or like eventually what a bonding curve became. It was a tool where you would buy a coupon with, say, Ether in the same manner where it's a monotonically, deterministically increasing supply, but the price would only decrease if the coupon is dispensed for some activity in the network. So whereas a bonding curve, which is you can just sell back in at any point in time. So it was very similar, which is some input happened that allowed us to congregate around a shared goal. And once we use this new coupon for services produced in the network, the price goes down. So it's sort of this feedback loop that I wanted to see happen. And then around 2017, the first iteration of token bonding curves, I designed it, I wrote down. And it was essentially, again, like I described, the concept of there being equity in a community that could allow them to curate information together, plus some form of automation of the protocol, and that's the bonding curve. And in the article, it is described exactly as it is today. With Ether, you buy some community token that stays in the reserve. You use this token to stake on information that you deem meaningful in the community, and to literally put your money where your mouth is. And at any point in time, you can decide to sell it back into the curve, take some reserve out, and then you can exit peacefully. There's always liquidity. And my belief was that this kind of simple mechanism is meaningful because you essentially undergo some kind of opportunity cost by locking up some valuable funds and then signaling it to your community or group. And that's where my direction of bonding curves came from. I wanted to see and create a curation community. And to this day, I wouldn't say there's been something that looked like this that exists on scale in the blockchain space. Probably the closest something like Steemit, but otherwise things like Meme Factory is probably close to that. Otherwise, bonding curves have primarily been used as sort of community fundraising or some kind of fundraising tools for specific goals, rather than it being used as a signaling tool. But I hope that time will still come. So to also add this for historical accuracy, I did write an article on this, which is, like who invented token bonding curves. And to my surprise, I only later discovered that it was actually a simultaneous invention. Bancor was invented in the summer of 2016, and they first announced it in February 2017. And they came from a different angle, a slightly different angle, but also tried to solve the problem of the long tail of tokens. We needed to be able to build methods of exchange that where, for my case, I wanted to see communities work amongst themselves. But on Bancor's case, it was like, yes, there will be many kinds of tokens, not necessarily for communities, but we just want to build some form of exchange that allows there to always be this kind of liquidity that doesn't work with a order book. And that was really great. I think it also is testament to how innovation generally happens sometimes. It's like things happen from different angles and different perspectives. And I love what the Bancor team has done and have contributed to this space. So, kudos to them. So I might be running a bit quickly, but hopefully that gives people time to ask some questions. But the historical context, as you can see, is like it was a set of evolutionary steps where the goal was for me to design something where you can have a continuous token model that allows communities to generate wealth together, but also then solve coordination problems through this method. It's like, what if we could automate an organization for the modern age, the modern information age? I think in the hashtag markets article, I even mentioned like, what if we put tokens into Reddit? And obviously, like today, we know Reddit is experimenting with tokens. They just obviously haven't yet tied tokens to information curation. Now, before I talk about the intent thing, I think as I have some additional time, the thing about the intent, the thing about which I think is still a difficult problem to solve, which is an open-ended question mark, is a lot of these ideas talk about adding economic cost to adding some kind of economic value and cost to information sharing. And I think that can sometimes obscure or cannibalize other incentives. Incentives like altruistic sharing or incentives for personal reasons. Like I use Twitter because I like reading, but also like sharing. People do Wikipedia because they want to enjoy the art of curating and editing and making a global encyclopedia. And if we only have economic signals, there's this possibility that you overcrowd the other incentives, especially with something like information curation. So what you can end up at is something where users serve the protocol and not the protocol serving the users. So I think that's still an open-ended question. Now, the final part that I want to touch upon before we get to questions is why I think this still matters. Because the reason why I got into the space and started thinking about all these ideas have always been at the base point, which is these are tools that we can use to empower people, to give people agency, and to give people access when their own societies don't necessarily give it to them. Whether you don't have access to financial means, to economic means, to legal means, or you're in a failed state, or a state that stops you from being able to do things. I first got excited about Bitcoin because I grew up in a country at the tip of Africa that didn't have access to PayPal until late, like early, like let's say 2010. It's like I didn't have access to financial infrastructure the same way that the first world did. that's still, I think, what we need to keep in mind. And that's why I'm really grateful that there are a lot of people here, like 74 people in this call, that are as excited about this stuff as I am, you know. So thank you to Jonathan, to Moritz for organizing this. And thank you to everyone listening. And I look forward to all the amazing talks by Ben, Paul, Jeff, Griff, Shruti, Shaun, and Michael. So let's just keep that in mind. Let's keep in mind why we're here. We want to give power to people. Thank you.
Thank you, Simon. That was awesome. We have a question here in the chat, and I also have one or two. Semi asked thoughts on the future of refungible tokens, NFT, micro ownership.
So a refungible token, for those who aren't familiar, it's if you tokenize ownership over a non-fungible token. So you allow people to buy into ownership with a bonding curve of, say, a piece of art or another form of collectible. I think it's a cool idea, but I think the context matters a lot, because if you NFT, the value of the NFT is the ability to also transfer it, right? So the ability to give it to someone else, or to buy it and sell it to someone else. If you tokenize ownership over it, then you, by virtue of making ownership fungible in it, you do slow down its ability to transfer. Like sometimes you would have maybe that in order to transfer it, all the participants need to agree to transfer it, for example. So I would still like to see people do more stuff with it. I still think it's a cool idea, but I think the context matters. Hopefully that's a meaningful answer.
Awesome. I have a question I want to throw in, and you touched on it in your talk, but I think there's still a bit of an uncertainty around the definition of token bonding curves. And at some point you had a bit of a Twitter discussion on what is a token bonding curve and what is not. Maybe that's an opportunity to throw it out.
Yeah. So I think as is the case when you're working with something new, naming is always a hard problem. And I didn't come up with the name bonding curves. It was the Zap.org team that looked at what I wrote on curation markets and said, this thing inside the curation market, this continuous token model, let's call this a bonding curve. I was looking for a name for it, that specific component, and then they came up with a name. I was like, this describes it really well. But obviously it's still confusing today, because it's only meaningful to us in a token engineering community or blockchain community, and people outside are like, I have no idea what you mean when you say the word bonding curve. And even inside our community, people might use the word to denote all kinds of automated market makers. And I think that's where I felt sometimes uncomfortable when people said Uniswap is a bonding curve, because I didn't want to take credit for that when I know the way I designed it in my head is that Uniswap doesn't use bonding curves, right? It's just another form of an automated market maker. So to finalize that question, to me, a bonding curve is, and I think Ben is also going to cover this in his talk, but to me, a bonding curve is you have the primary focus on a bonding curve is this concept of a token supply growing and shrinking based on there being a reserve attached to it. So if you have one token, you put it in, it mints new tokens as part of its process. Whereas other automated market makers might merely serve as an exchange, and it would look like something like a bonding curve, but it doesn't have the component where you're minting new tokens. And I think that's still sort of the core thing that I think is important, the aspect of the bonding curve minting new tokens.
Perfect. Thank you. So that was already all the time we had. Thank you so much for coming on, Simon. Okay. The next session is, sorry?
No, I'm happy that it worked out perfectly in the Swiss manner.
Yeah, that was on point. So Ben, your session is next. I want to quickly introduce Ben. So at some point, because I'm learning coding, I asked Ben what kind of coding programming languages he speaks, and then he came up with a list of I don't know how many, like 25 languages or so. So Ben not only is a rockstar coder, he's a CAD contributor. Very advanced CAD coder. He's originally a mechatronics engineer, has a background in bio-inspired robotics and control. controls engineering, all of that good stuff that's very helpful for token engineering. And he's going to give an introduction on, that's a bit more beginners focused. And I want to, just before we start, put one thing out there. We want to show our faces in this community, and also not only between each other, but also to the outside world. So I'd love if everybody could just like switch on his or her camera, and then we can take a group picture as well. Just want to throw this out there. Go ahead, Ben.
Thanks, Jonathan. Can you see my presentation?
Yeah.
Great. Okay, I'm going to be giving a technical introduction to bonding curves specifically for beginners. And this is to give you a basic overview of the landscape of bonding curves. And a few of the goals that I'd like to achieve with this is that by the end of this, you will be able to speak to your friends about bonding curves. You'll understand a bit of the lingo that's involved. You'll get an idea of how bonding curves have evolved and been extended upon, and also gain confidence generally in token engineering and being able to explore the space a little bit deeper. Bonding curves are a very core component of a lot of token engineering systems. And some of the basic properties that you've learned a bit about already from Simon are that you've got a function, which is at least a function of token price and supply. It is monotonic, which means it's always increasing. And it is also predictable or deterministic. So given the same input, you'll have the same output. But as you'll see in later examples, there are lots of variations of this, and this is all where it all started. So you could consider this a monotonic bonding curve. So there are a lot of misconceptions about bonding curves, mainly because of the sort of applications that they've been used for. So as you saw, the curation markets as well as automated market makers being developed alongside each other. A lot of people, because of the use of bonding curves for funding or exchanges or various other funding mechanisms, people think they're Ponzi schemes. Uniswap has also been sort of talked about as a bonding curve, and it's kind of a bonding curve. So you'll see some of the sort of properties where it differs later. And I'd just like to give you a little bit of a background on a few simple sort of blockchain or crypto economic concepts that might help understand what I'm going to talk about now. So bonding curves with the introduction of Bitcoin, blockchain with the introduction of Bitcoin introduced the idea of scarcity in the digital domain. So a classic example of this is having an apple. It's unique, it's in the real world. If you take a picture of that apple and you then put it in the digital domain, it is no longer guaranteed that that is unique. It can be copied, shared, spread. And blockchain introduced a mechanism to solve this double spending problem of being able to use a token or something of value more than once. Liquidity, this is a sort of nice way to visualize it in the case of an exchange. You've got willing buyers and willing sellers, and this introduces the idea of liquidity. So liquidity is the availability of liquid assets for transaction and trade. And bonding curves can be used to introduce liquidity for systems. And here is the concept called price discovery, which is, I think, microeconomics, which is the way demand and supply interact with each other and reach an equilibrium point for pricing of some sort of commodity. And bonding curves have been used and can be used as a primitive price discovery mechanism. I think this is probably most prominent in curation markets. Okay, some basic terminology or lingo. Some of these are concepts that are not only for bonding curves, but also token engineering. The idea of collateral and reserve. So collateral is the value that is provided in exchange for a supply of tokens. And the reserve is the pool of value backing the token supply. So in this chart here, you can see a basic curve. This isn't necessarily a bonding curve, but underneath you can see the area of under the curve, which would be a sort of integration by parts, and this green area represents the collateral that is backed by the bonding curve. So the tokens that are supplied along the x-axis would have a collateral backing, being the area under the curve. The idea of market cap or market capitalization is something from the sort of financial world. It's nothing new, but in the case of bonding curve, it would be the spot price multiplied by your total token supply. And your supply is the tokens issued in exchange for your reserve collateral. So I'm going to attempt to draw, I think. Zoom will let me. No, it doesn't seem to let me. Okay. A bonding curve function. This is your function that describes a relationship between your token price and your token supply. The spot price is the value of a single token at a point along a curve. So in this diagram here, you can see the current price, and if you were to buy a supply of 10 tokens, you would exchange that for a value in collateral, which would be the highlighted area under the curve. So this is not something I'm going to dive too deep into, but there are a number of formulae and properties of bonding curves that are sort of common properties between a number of different implementations of bonding curves. And one of them is the reserve ratio. And this is the ratio between the reserve or the area under the curve to the market cap, where the market cap is a sort of, yeah, it's the value of your total token supply multiplied by the spot price. And here you can see how varying a parameter such as your reserve ratio can have an effect on the resulting bonding curve. The idea of slippage and price sensitivity, this would be the effect of a token transaction on the spot price. And I think all you need to know here is that the reserve ratio and the inverse leverage ratio, both of these sort of properties affect how sensitive your pricing mechanism is to trading and transactions. And you can, if you were to go and use Uniswap, you would be given a percentage, which would indicate what slippage you would get from transacting. A number of the mechanisms and automated market makers and bonding curves have the idea of an invariant. This is basically, it's a property or relationship that remains constant. If you did basic geometry, triangles have a number of different invariants, and the same holds for bonding curves in a different way. So what is a market maker? It's a mechanism that creates or provides liquidity in exchange for a given token. And coming up, you'll see the concept of automated market makers. So when you're designing a bonding curve, there are a number of different properties that you have, or parameters that you can design around. And they all have different effects. And it's almost a bit of an art, I'd say. So some of the parameters are listed over here. I'm going to go into a bit more detail about each one. Okay, firstly, the idea of time. So bonding curves, a nice analogy for them is a sort of, it's a pool of collateral. And over time, this collateral can change, it can aggregate over time. So there are a few examples coming up in the later presentations about the idea of voting and how people's conviction in a given vote can collect over time, and also token vesting. Pricing, so price differences, basically on the left you can see a bonding curve as we saw earlier, a very basic bonding curve where you've got the same price for buying in as well as selling out. if you were to introduce a different curve for buying in and selling out, you could introduce the idea of taxation. You could disincentivize bad behavior by having this sort of cost for selling out of a market or bonding curve. You can also decide to choose what collateral you want to be held in your bonding curve. So the bonding curve collateral pool, if you were to have Bitcoin in that pool, you would have a very volatile market, and it wouldn't necessarily be truly representative of some idea or thing that you're trying to curate. In the case of a curation market, you would probably want to rather use DAI, which is a stable sort of US dollar tethered or token. And also, one of the questions that came up earlier was fungible and refungible tokens. And this is, once again, some parameter that you would be able to choose. Your supply, basically just whether it's capped or uncapped. So if you have a cap of 10 million tokens, that would introduce different sort of user interaction and behavior than if you had an uncapped supply that's for a market that is intended to be very long-lived. You can choose the function of your bonding curve, and this is your relationship between your price and token supply. You can sort of try and design or drive different actor incentives, and some of the dynamics that you introduce with different functions can only truly be fully understood with modeling, which is a topic I'll briefly cover, and I'm sure some of the block science team will dive into a few deeper discussions around modeling of bonding curves and token systems. Here's a few basic bonding curves: a basic linear curve, quadratic curve, and the common stack curve, which I hope I got right. So you can also, a token engineering system often has sort of a very modular makeup where you could compose different bonding curves with different inputs and outputs. You could have different parameters for different phases of your project or system. And this is sort of a very useful feature of bonding curves, which the common stack augmented bonding curve uses very well in composing a sort of more complex system around voting. So automated market makers and liquidity providers, are they bonding curves? So Uniswap, Bancor, and Balancer all describe some form of mathematical relationship between two or more token pools. They share some properties with bonding curves, and they all have a mathematical pricing relationship with some form of invariant. So Uniswap is described as an automated liquidity provider. They have a relationship described by the function there, where K is the invariant, X and Y are the reserve balance in a token pair. And this relationship gives it certain properties, which we won't get into, but it does share some of the sort of same features of bonding curves. Here you can see a basic model as modeled by Marcus from block science, where it's as your sort of your reserve of one or other of the other tokens, whether it's in this case Ethereum or DAI, as that reserve changes, your price along this curve is adjusted to match this relationship. So Bancor is described as an always available constant liquidity source. It's also got a function that describes some of its properties with an invariant. In the case of Bancor, this invariant is the reserve ratio. So Balancer is a sort of portfolio manager, and it's difficult to see from this image, but it's a 3D image, and it's no longer your sort of basic idea of a monotonically increasing bonding curve, but introduces more sort of dimensions and has some of the same properties. So it extends, it's a generalization of Uniswap's constant product rule and allows two or more tokens, but with arbitrary weights. So if you had a portfolio, or let's say an investment portfolio, and you've got different tokens that you want to keep balanced within that portfolio at different percentages, this would allow you to do that. So what are some of the limitations of when designing bonding curves? So specifically it comes around because of solidity and the Ethereum virtual machine. Some of the mathematics becomes a bit more complex to implement. You get overflows and underflows, you get front running, you get batched processing of transactions to try and avoid slippage. And here's a picture of some bonding curve code for a basic linear bonding curve. So this is probably the simplest implementation you could get for a linear bonding curve. And basically all you're doing is you're implementing an integral of your bonding function and an inverse integral of that function. And this allows you to calculate both the buying and selling prices for a set number of tokens. So bonding curves, when integrated into token engineering systems, become complex. This is not necessarily a limitation, but it is a limitation if you do not model your system and you do not simulate it properly. And I'm sure you'll hear more about this later. So more and more the engineering practice, basic engineering practice, has been brought to token engineering. And this has introduced a sort of more iterative design cycle where you have your implementation, you can then have a carbon sort of copy model of it. You can simulate the behaviors of your model and try and inform the design and implementation in the real world with different actors, whether it's different users or mechanisms or other systems that you're integrating with. So why would you want to do this? This allows you to validate your designs, test for how robust your system is, find edge cases, check how sensitive your system is to small changes in some of your parameters, and find out what the bounds of your system are. Some edge cases are more obvious than others, and modeling helps to find those that are more complex or less obvious. So how is this done? You can do active modeling and simulation. The CAD framework is an open source library that was built by Block Science and allows you to do simulation of complex systems with various things like parameter sweeping, which is changing a parameter and seeing what effect it has on your system, and running Monte Carlo methods, which allow you to run very large experiments on your system. For example, here you see a basic experiment with different parameters and some sort of more Python data science type outputs from it. So what are bonding curves used for in the wild? All sorts of things, which you're going to get a whole range of examples in the later presentations. Some of them are things like system interfaces, voting, community currencies, and funding is also part of this. Is probably one of the ones that have been sort of gotten most of the attention, but there's a lot going on in the space. So what are the trends? Application of engineering methodology, more and more degrees of freedom in your design choices. More variables are being introduced, such as time, and they're being used as a modular part of larger systems rather than simple funding mechanism. Just like to thank contributions from Angela for the presentation. And there are a bunch of resources, the Token Engineering website being the first one, the CAD discourse channel, and this presentation is on GitHub with a slightly more extended version if you want to read it. And you can send any questions my way. Thank you.
Thank you, Ben. Unfortunately for this session, we don't have time for questions. If there are any urgent questions, please post them in the chat now. Otherwise, I'd move on to Paul. Paul, you ready to go? Awesome. So Paul I quickly introduce you there. So you're a technology entrepreneur. You've done a whole bunch of things. You're the founder of Linum Labs, the founder of Molecule. And what I find exciting about Molecule is that you guys have actually launched a system in January called Catalyst, I think, which you're going to speak about today, which is a protocol providing a new distributed ownership structure for pharmaceutical compounds. And yeah, I think I'm both looking forward to hear about how you went about, your bonding curve design, and also like what, how the launch went, and what you're trying to do with this project.
Awesome. Yeah, Jonathan, thank you so much for the invitation to speak, and thanks for the kind introduction, and yeah, also for organizing this. I think it's really great to bring the community together on a regular basis. I think that's really important. Cool. So as Jonathan already said, I'm the founder of Molecule and Linum Labs, which was kind of the software development house that had built this first implementation around Molecule. Before I'm going to jump into the depth of what we did and what we launched in January, I want to say like why for us token bonding curves are a really cool use case and application in this context of what we're trying to do with Molecule. Our kind of broad goal with Molecule is really to a first attempt at decentralizing pharmaceutical and biotech R&D, specifically in the early stages. And I think, if anything, the current healthcare crisis that we're witnessing is putting an enormous new pressure on finding quick and efficient ways on how we discover medicines and new treatments. And that's something essentially that we stand for. Some very brief background. A lot of you might be aware of this, but developing new pharmaceuticals has never been more slow, expensive, or risky than it is today. The average time to market for a drug today is over 10 years. It can cost up to $2.5 billion in development to bring a new drug to market. It has a really low chance of success. The current efforts, for example, that we're seeing in coronavirus vaccine development, where even bringing a new vaccine to market within 2 years is completely unheard of. But at the same time, we believe that the time is right for newer, quicker development models. And we think that decentralization has a super core role to play there. But because of the way the system works today, drugs are getting increasingly expensive and fewer drugs are actually coming to market. And why is that the case? Our thesis is that drug development is essentially where software development was 30 years ago. It's extremely proprietary, so it's all driven by patents. It's very closed off, very secretive. And then one of the big issues that we find in the industry today, that there's a big lack in early stage funding. And when I first started looking at this topic, and I met Simon in 2016, and he had these ideas around curation markets. And there's this huge similarity in curation markets and drug development. So this is essentially the very classic pharmaceutical development pipeline. You have drug discovery. First, you start out with basic research, then you discover a new molecule. You move that molecule into the preclinical phases, then phase 1, phase 2, and phase 3, and then it comes to market. And here at the bottom, we have classical innovation cycles within companies or externally. And essentially, you start with a very large funnel of new molecules. And now you have to filter out what is going to work, what works for which use case. And throughout the history of drug development, for example, there have been many, many molecules that have been developed that later on someone else discovered that, hey, actually, this could be used in a different use case. And this is eerily similar to like how curation markets are designed, or how we curate information more broadly. And I really enjoyed what Simon said in the beginning of his talk, that this combination of reducing information asymmetry through the distribution of equity to owners, because it creates new incentive and new behavior structures. This is a pretty old slide that I've used a lot, but it's essentially how we could kind of then got onto the topic, this combination of so drug development is always based on IP and patents. Could we attach patent value to a non-fungible token? And then in the second step, could we use that now, that on-chain asset, to raise liquidity around the development of a new drug? And another really interesting element that this has is that bonding curves as a whole can serve as these open source prediction markets. So positive data increases the price of an asset, negative data decreases its price. And this solves one of the principal problems that you have in drug development, that there's a strong principal agent problem that if you're developing a drug, you only want to release the good data. And there's something known in the sciences more broadly, which is called the reproducibility crisis, that for a lot of early stage scientific development, there's no incentive to publish negative data. And then if people are trying to reproduce a specific scientific result, they're often not able to reproduce it. And we felt for a very long time that bonding curves can, or new automated market makers can play a key role in overcoming some of the challenges in the industry. Overall, just to brief recap, what are we trying to do? Essentially, we're trying to move IP out of companies and out of universities, specifically universities at the moment, into an open ecosystem where drugs can be developed openly and collaboratively. So essentially, it's a two-sided, our protocol is a two-sided marketplace of drug developers and patients and investors. This is a long-term vision of what this might look like. You essentially would have a marketplace where you see rising and falling prices on different assets that are in development. The researchers working on them, essentially really creating collaborative workspaces and funding environments for these new assets. So as Jonathan said, we launched the first experiment using bonding curves and this exact use case on the Ethereum mainnet in January. I'm really saying it was the first experiment because I think we realized going into that there was a lot of things that were still missing. And what I really want to share with you over the next, over the next remaining 10 to 15 minutes is some of the insights that we took away from that. First, how the system works, and then also the insights and learnings that we took away from that, and kind of what's next on our roadmap. So just a very brief recap. So what we launched is a system called Molecule Catalyst, which in its most basic form is a Kickstarter for very early stage scientific research. But the goal is obviously that instead of with a Kickstarter, you normally either you're just doing it for the cause of it, or you receive a share, not a share actually, you receive the product that comes out of it eventually. In our case, our goal is really to give people ownership in the IP that they're funding. And so the way that Catalyst worked is funders would make a contribution into Catalyst. The funding would be forwarded to the researcher. The researcher would then contribute his research data into Catalyst. And in return, the funders would receive project stakes, so ownership in this new research project. The first project that we kind of pioneered this with was a high impact clinical trial to study the effects of microdosing psilocybin with the University of Toronto and the Toronto Center for Psychedelic Science. Pretty fringy topic, but also I think it's a very cool overlap with some of the ethos of the crypto community. How it works basically was, so the fundraising mechanism itself worked by a bonding curve that had a 25% tax. This means that 25%, like if with 100 DAI contributed, 75 DAI would go directly into research funding, and 25 DAI would become a project stake that essentially now creates a permanent liquidity pool and a measure of value around this particular research project. And this is just an example how essentially the market builds up over time as more contributions come in. So in return, anyone could contribute DAI openly. There was no KYC. Anyone could really kind of participate and become a co-owner in this research project. Here, just a quick recap. So the token prices, so it was a linear bonding curve. We chose a linear bonding curve because it was one of the simpler designs to really experiment with and to provide clarity also to the users. We also wanted to design a system that was reasonably fair to everyone contributing. So less like one of those extremely exponential bonding curves, but really achieve a fair distribution over time. So the token price increases linear with supply. The early contributors obviously receive more tokens. The token represents your stake in the reward pool. So legally speaking, with this first project, we couldn't attach any property rights yet. On the one side, this came from the university because they wanted all of the data that came out of this project to be open source. But it was also one of the big problems that we encountered. Like if you're dealing with real world assets, like you need to engineer, you need to do the legal engineering. And this contribution rate now creates an immediate funding liquidity. And the taxation mechanism that we implemented also prevents pump and dump behavior, because it would take quite a while with a 75% taxation to actually, to get it to a break-even point again. But we felt at the time that this would also create very strong incentives for the early contributors to essentially become, how do you say that, supporters or like vocalists or like fanboys that would now convince other people to start contributing. Again, this is kind of just a technical diagram how this works. So the contributions will go into a research funding vault. There's a timer that was implemented in smart contracts that we ran that a certain milestone would have to be reached at a certain point in time. And then only then the researcher could withdraw their funding. And if that funding milestone was not met, then the accumulated research funding is returned and can be exchanged again for project tokens. This is also a similar design as a Kickstarter has, in that sense that if you don't reach your funding goal, obviously you can't start a clinical trial without the required funds. So if that is not reached, then the funds are returned. We got amazing support from the community when we launched this. I think it's one of the first like complex live bonding curve based systems on mainnet. It lends itself quite well as well to, I think, what Jeff and Griff are going to talk about later, which are augmented bonding curve designs. I think this, in this sense, is a relatively simple first augmented bonding curve design in the world. We got hundreds of unique interactions, really great feedback from the community, but we didn't get to our target, which is obviously the bigger goal of what we're trying to achieve. So we reached about 10% of the initial target, which came in plus minus, this is just a screenshot from the campaign, which came in plus minus to under, just under $5,000. And in the context of what we're trying to do, that was a big success. But we also have to realize, like, hey, if we're trying to fund early stage drug development, like this is not like, we're not helping the scientists like this. And so we took a lot of learnings away from that first, exercise. And one of the really big learnings that I want to share with you, oh, and by the way, if any of you contributed to the campaign, by the way, you can withdraw your stake at any time. So essentially all funds as well have been are being returned to whoever contributed to the campaign. I explained partially to other people in the community, but also to ourselves, we had a lot of internal discussion around what we would do next in this regard. And I think this is quite telling in terms of designing a bonding curve based system. And now I'm really talking about use cases. I mean, we can do all the the modeling and all the token engineering that we want. If your user base doesn't fundamentally overline with what you're trying to do, then no cat model can help you with that. and so this is kind of and I mean, I think we could have seen some of this coming, but I also always think you just need to experiment and just put yourself out there. And that's how you move along, and so just consider this as a Venn diagram. I mean, it's pretty self-explanatory. This is funding people that are interested in funding biotech and psychedelics. And then there's people interested in crypto. And now within the crypto community, you have a portion of the crypto community that are native DAI users, or native DeFi users. They have MetaMask, they have DAI in their wallet. You'd be surprised how many people don't even have DAI. I'm continuously surprised. And then within, I'd say, native DAI users, you have an even smaller circle that are interested in bonding curves. And this is kind of where we chose to launch our first experiment. And we just realized that is a very small target area. And I think it's reflected in the campaign. And I think the success that we had in the campaign. But yeah, I think that was a really good insight for us. And for us, I don't think we've discarded from that exercise that this general notion isn't going to work. What I think needs to happen is these circles need to grow quite a lot in order for this whole thing to come together in a better way. So yeah. Some other insights that we had, I'm just going to run through these. So when dealing, yeah, it seems obvious, but maybe not so obvious, when dealing with real world assets, really focus on the legal engineering first. So I think for a lot of fringy crypto-esque use cases where you don't need legal engineering or where you're not dealing with the real world assets, go launch ahead and experiment. But at the end of the day, like what we are trying to do is to get people really to benefit in the upside of the potential IP that is generated. If we can't guarantee that, it's a hard sell. A second one, I think that is build a community around an asset prior to launch, or build a community around what you're trying to achieve with your bonding curve first. And then try to launch the curve internally first, rather than just fully publicly. So growing something within a community where the community can take over governance functions. In our case, this could have been, for example, have a community of researchers that helps co-define evaluation and a starting point for the bonding curve, rather than us as a team having to kind of define these parameters, and sometimes just feeling a little bit out of our depth. Don't underestimate the marketing efforts required to get a bonding curve active and liquid. It's an enormous amount of marketing. It's like it's crowdfunding in essence, or like in many cases. And we as a team, we had to realize that if we're going to spend 60-70% of our time in the next couple months marketing for this one experiment, we don't really prove that much for it. And marketing isn't our core, like that's not our core expertise at the moment. So that was another big takeaway. We also had some takeaways on just on the insights on UX and UI. Again, user experience for non-DeFi, I'll say non-DeFi native users and use cases is still a massive problem. Like, what the hell is DAI? How does MetaMask work? Onboarding non-crypto native users, in our case, scientists, or even just people that are really interested in like supporting psychedelic research. We did a bunch of Reddit threads, and people were just like, but how the hell, like, do I get from here to here? And of course, you can only send so many guides, but in the end, you have to be realistic around, around onboarding the masses at this stage. Another surprising insight for me was the UI for bonding curves was surprisingly not a big issue. Like, people just kind of like trusted in the system, and they were like, okay, this seems good. But I think we expected when we launched it that there would be much more apprehension towards UI of like the users understanding what is happening here. But that was surprisingly not that big of an issue. We have to say as well that we invested very heavily into good UI development for it, and a huge shout out to Michal Schachman, who was our lead UX and UI designer on here, did an amazing job. Last point, the DeFi liquidity for non-crypto use cases, in my opinion, is also still way too small. There's just not enough liquidity moving around in the ecosystem to really say, you know what, let's finance a real estate development project. I think we're still at a stage where we're going to struggle with these non-crypto-esque use cases where we're not trying to sell, where we're trying to connect this with the real world. Maybe just a very quick rundown, like what's next for us after this first experiment. So we actually had a host of research projects from various universities. So this one with Toronto, we have another one with the University of Copenhagen that we were planning to launch with Catalyst. Now we just realized that, hey, this partially due to the UX UI problem, partially due to the liquidity, this isn't the best fit. So what's next for us is really that we're initially building for that user base. We're saying, let's focus very heavily on this user base, because this part we can do. We can always bring this in, but let's build this side first and take a more Web 2.0 approach and do private syndicated financings first. This is what you could consider building that initial seed community, but saying, you know what, like bank accounts for the time being work, and equity is still a thing. The second is get the legal engineering right, something that we're going to invest in quite heavily. Then step 3 is create more research and patient communities, a research and patient community development around the individual assets before taking them the full 9 yards to like a public listed bonding curve. And then slowly start reintroducing Web 3.0 principles, start decentralizing these communities in a similar way that Reddit has done this, saying we have a community, we can start decentralizing that as opposed to the other way around. Start implementing token engineering, and then really go into a more open market approach again and DAOs. And this works for us together quite well. I don't know how I'm doing on time, but yeah, that was it. Please feel free to email me if you have any questions, if you want to collab on anything.
Perfect. Thank you, Paul. That was also perfect time-wise. So everybody, if you want to get in touch, paul@molecule.to is the email address. I actually had one question, but I'm not sure if you can answer it in, like, say, a minute, Paul. You basically said that you wanted to have a, be fair. You took a linear bonding curve because you wanted to be fair to users. I think that's what you said. But I also know you experimented with sigmoid curves. And, when you talk about fairness, I think, if you really dig into it, then you could probably argue that, later users, they have less risk and there's dynamics in the development of this compound. Can you just, like, maybe say a few sentences about different, the trade-offs or in choosing a specific bonding curve design? I think that I would find that insightful.
Yeah, I think I actually have I have an article on that, which is called Token Bonding Curve Design Parameters. It's a little bit older already, but it talks about some of the trade-offs.
Perfect. So
yeah,
what is it exactly called? Then maybe people can just reference that.
It's called Token Bonding Curve Design Parameters. I'll post the link into the chat just now. But I mean, to answer your question, I personally feel that, like, a linear bonding curve has, like, a relatively slow and steady growth, as opposed to a sigmoidal curve, which can have a very slow growth initially and then has a strong growth period. We made this choice because we wanted to experiment with a simple design first. There's a saying that, like, don't innovate in, like, too many areas at the same time. Yeah. We felt we were already innovating in so many that, like, a simple design seemed to make more sense. I think it's entirely use case dependent. What type of curve you choose. I would definitely try and model it with, like, the real world. Like, does this make sense in the real world? Yeah. I do think, though, for other use cases, like if you're trading memes, you could because there's a fundamental question there. Like, if we're trading the ownership of a meme, like, what are we? Like, what is this? Is it a piece of IP? Is there a retainable value? Is it a collector's item? And in those cases, like, I think you can go for very crazy designs and just, like, experiment. Yeah, I don't know if that fully answered your question.
No, perfect. Thank you so much. I wanted to add, I think what I like about this project specifically is that it's very pragmatic. You guys, some of your potential customers on your board, I'm not sure exactly if that's right, but I think a lot of projects could have saved themselves a lot of troubles if they would have approached it, from a market perspective, like you guys did. So next up is Jeff from the Common Stack. Jeff is a token engineering researcher at the Common Stack. The Common Stack doesn't really need an introduction. It's one of the most, I think, ambitious but also exciting projects out there at the moment. And he's also publishing like crazy, like, like you could spend the whole weekend binge reading his articles, and you should, I think. And he's also working with Block Science on a couple of things. And Dr. Zargham, who's going to present later. So we're looking forward, Jeff, to the talk on the augmented bonding curve design archetype.
Awesome. Let me just share my screen here. Can everybody see the presentation okay? Cool. Well, first off, I'll just make a note that my laptop is having some audio encoding issues. So if there is any issue with my audio, just feel free to drop a message in the chat and I'll get closer to the computer, but I'll assume that everyone can hear me from this point. Cool. So yeah, I'm here to present the design archetype of the augmented bonding curve. And as Paul mentioned in the last conversation, I think all of the presentations today are on augmented bonding curves in some way or another. And I think that the big question is, what makes a bonding curve augmented? I got into this space reading a lot of the work from Simon, from Paul, from Zargham as well. And I think naming is a continual difficulty in this space, as Simon can attest to. Yeah, the augmentation in the bonding curve in the context of the Common Stack is these properties that are formally defined with mathematical invariance. Ben talked a little bit about invariance in bonding curves and automated market makers. But we have this invariant coefficient that is, some ratio between the supply and the reserve and kappa and a few other terms in these invariants. So the great thing about invariants is they provide mathematical stability on which we can do further token engineering. And the token engineering allows us to integrate these context-appropriate mechanisms. So in the common stack, for example, we have an initialization phase, which Paul mentioned could benefit the next launch of a molecule bonding curve. We can integrate entry and exit taxes. We can integrate vesting periods and all sorts of other mechanisms that build the kind of usefulness of the bonding curve to a context in which it's used. So this brings us to the engineering design process. And as I'm sure some of you have seen before, this starts with the mathematical foundations. Then we go into modeling how these flows move through a system in a stock and flow diagram. And then plugging those into the CAD Python framework allows us to simulate and determine all of the ways that these systems may react to various agent behaviors, and also give us important insight into where they may fail moving forward, so that we can design appropriate failure protection into the mechanisms before we go to code and launch these in a real world environment. So diving a little bit into the math, this can be a little bit overwhelming, but if you are of the mathematical bent, there's a lot more under the hood of the common stack augmented bonding curve. But essentially what you see over and over is this invariant V naught, or the power invariant function. So we have a deposit to mint or a bond to mint equation, the burn to withdraw equation. Always this invariant stays constant. And on that invariant, we can design higher order mathematics that are stable because they're resting on this mathematical invariant. And when we turn this into the system stock and flow diagram, it's important to note that bonding curves on their own aren't actually anything. They're a value transfer interface. But where it gets interesting is when you integrate it into a system that can use it for something. So this is a system diagram of the common stack use case. So in the top left here, you see the bond to mint and burn to withdraw mechanisms that we just looked at the math at in the previous slide. So when a user inputs reserve, say in DAI, that is bonded to the curve, and some supply of tokens is minted and issued to that user. When that user burns the supply, he can or she can claim a portion of the collateral. As we discussed, the withdraw is taxed, and that tax goes into a funding pool in the common stack scenario. And that funding pool is actually used to create incentive for community members to create or carry out work proposals. So whatever work needs to be done in that community, whether that's producing open source code or cleaning up beaches or housing the homeless, this funding pool is fed by this withdrawal friction or exit tax. And then from this CAD model, we can plug it into the data science framework, and we can start modeling and testing our assumptions. So what you see here on the blue line is the invariant of the bonding curve and also the price from the mathematical formula. And then all of these dots are sampling. So basically we ran this through parameter sweeps and various agent behaviors, Monte Carlo analyses, and we can see that the observed data, so when we test this in the system, all of these, we're finding that the invariant holds, and we're finding that the price stays on the curve throughout. So we're basically just verifying our assumptions that these invariants hold under various conditions when we actually use the bonding curve. So why are invariants so important? Invariants actually enable stable design, and we see this all over the place. In civil engineering, Newton's laws are used, like balancing forces. When we're creating a building, we need to make sure that it doesn't fall down. So we use formulas like force equals mass times acceleration. In electrical engineering, we have Kirchhoff's laws, B equals IR, and all of the higher order mathematics that can come out of that invariant. In token engineering, we have Zargham's laws. So this is the bonding curve invariant on which we can design, again, derive higher order mathematics. And this essentially enables us to engineer economic space for agent interaction. So what can we do with economic space? This essentially allows us to create incentive landscapes where you can encourage beneficial behavior in your community. So in the example that we just spoke about in the common stack, taking profits or selling out of the curve, you pay an exit tribute. So that costs you money. You're up on this hill. We're not saying you can't do it, but you have to exert some energy to get up that hill. On the contrary, completing work proposals in this community is actually incentivized. So you'll see this ball as an agent in the system. It's more likely for this ball to end up in the valley where it's incentivized. It's rewarded with tokens for completing work proposals as opposed to exiting the system. Now, we're not saying they can't do that. They certainly can, but they're more likely to be following the incentivized behavior rather than the disincentivized behavior. So this is a tool for internalizing externalities in a community. Another example you could look at this is in carbon offset credits. If you pollute, you have to pay. You climb this hill. We're not saying that you can't climb the hill, but we're saying we would prefer you to cut your carbon costs and be in this valley here. And actually the fees, the taxes that are incurred on the people who are polluting are subsidizing the people who are cutting their carbon footprint. So this is essentially a tool for aligning incentives in the economic fabric of our societies. And a lot of people ask, will this work? These are pretty radical claims. This is a brand new design space. So we look to real world engineering parallels where this already works today, and we can see whether this will be a viable tool for us in aligning economic incentives. So the math for the augmented bonding curve is actually derived from something called Lyapunov functions, which you can look into. It's quite deep and abstract, but essentially they're energy conservation equations. So this is like defining the gravity for a system. And used in swarm robotics for actually decentralized multi-agent estimation and coordination, which is, believe it or not, what we are essentially doing in the crypto space as well. We have decentralized control of multiple agents, estimating, so in other words, determining how we're going to evolve these community structures and how we coordinate in a decentralized fashion to move forward the goals of our community. So in the example of swarm robotics, you can see here these drone swarms. So each drone doesn't have an individual human pilot. They actually have a complex algorithm where maybe you deploy these 7 drones to cover an area with a stable Wi-Fi signal. So these drones essentially sense each other. They can pick up the Wi-Fi signal from all the drones around them. And they use this Lyapunov function to essentially slide into using this gravity equation to the appropriate place where they are providing best coverage. So that's actually, if we go back to this diagram, you can picture this dot as a drone, and as it's detecting its optimal spot for Wi-Fi coverage, it kind of slides into this optimal spot for it to provide that coverage. So we have lots of established engineering tools and practices that we can now apply in this new economic realm and align incentives in new ways. But people aren't drones. So how do we know that they're going to respond to these incentives? So essentially, if we think about designing economic space the same way we design physical space, we have all sorts of architectural design. So a parking lot is a good example. We paint lines on the ground and we say, hey, cars, if you park within these lines, then we'll have order and we can fit more cars as opposed to everyone just parking everywhere. And in most cases, this does help guide useful behavior. Cars generally follow the painted lines and we have some semblance of order in a parking lot. But of course, in some cases, this isn't the case. Humans are unpredictable. Humans can do basically whatever they see fit. But that doesn't mean that the architectural design of the parking lot is not a useful design framing for us to use. And we can do this now in the economic realm, despite the fact that people are sometimes irrational or unpredictable agents. So essentially, we're building towards a future of aligned incentives. This is a great diagram that Kevin Owocki at Gitcoin put out in a tweet thread a few weeks back on aligning the moral and the economic landscape. And his point was that the needs of our societies, in other words, our moral landscape, is often quite different from the economic incentives that we have in our capitalist societies. So the bonding curve is essentially a tool that we can use to shape our economic landscapes and the incentive fields that we apply in those economies to more closely match the moral landscape of our communities. And that's not saying we need to do it at a global scale, at a national scale, but we can do it at a community scale, and it can scale up from there. So this is a way that we can really align these incentives of actors in an economy to match the socially beneficial outcomes that are desired in our communities. So to wrap up, bonding curves are augmented with invariants and contextualized design. These invariants allow for token engineering modeling and simulation, which is an essential part of these complex tools moving forward. And they enable the use of established engineering tools, things like low-pass filters, Kalman filters, Bayesian analysis, all of these engineering tools that have plenty of precedent in the real world today, we can now apply in the crypto economic realm. And this will allow us to architect economic space, which opens up an entire new design space that warrants much further exploration. And a lot of the projects that are in this presentation today, in all of these presentations today, are really pioneers in exploring this space, and there's much more to come. So thanks for your attention. And if you have some interest in diving deeper into the mathematics or some of the applications of bonding curves, one that isn't presented today is the Red Cross Community Inclusion Currencies. So happy to provide some links to dive in deeper there. And if anyone is interested, I have a bit of time for questions, I believe.
Yeah, thanks, Jeff. Are there any questions for Jeff or the augmented bonding curve design archetype? Where can we find the links? Someone is asking.
I will share the presentation with Jonathan, and he can make sure it goes out perhaps with the recording.
Fantastic. Then let's see. Somebody's asking, morals can shift over time. How do we handle that? And that was very close to a question came up before, which was about how do we determine good or bad outcomes? I'm not sure if that's a question that can be efficiently handled. If you have thoughts, please share.
I can give a really, really short answer. So essentially what we're designing here are cybernetic systems. And cybernetic systems are steered by humans, but when we steer them, they're also steering us. So they're second order cybernetic systems. And that's a very good point, because if we just set the incentive and then we can't change it, then we'll be stuck in whatever the ethos of the time is. So these systems need to evolve. And this is where things like conviction voting could come in. So in the Common Stack example, we have the ability to upgrade these systems through the governance of the commoners in these systems. The community members, through their token holdings, can evolve the incentives and the goals of this community, which of course is very important. Whenever you have humans in the loop, we need to make sure these systems can evolve and continue to represent the needs of that community.
Awesome. Thank you. I would take the 1 minute to make a quick announcement. So we're looking for somebody to join us at Token Engineering Switzerland, somebody who's interested in organizing these awesome events with us. And the benefits really are you get introduced to all of these beautiful people and speakers, and really can network very efficiently. So if you personally, or if somebody in your network might want to join us, Moritz and me, to organize the third event, probably in August, then yeah, get in touch. Just wanted to put this out there. And then next speaker is Griff. Griff is also such a well-known thought leader in the space that he doesn't really need an introduction. He's been around since the early days, since the DAO. I think, Griff, you've been a community manager at the DAO. You founded, and you were very much involved in cleaning up the mess. You founded co-founded the white hat hacker group. And you now dedicate your life to the Commons Stack, and we're looking forward to your presentation.
Thanks. Thanks a lot, Jonathan, and thanks for getting us all here. This has been an amazing event so far. I hope I can continue it. We'll see. So at the Commons Stack, our main mission and the final product that we want to produce is something that will take any community that wants to create funding for public goods, basically create a sustainable system for things that are generally considered non-profit causes. And have any normal group come in, have their hand held, and be able to create a system that will allow them to create value, the value that they want to create. And so I'm supposed to give a case study of this, but we haven't gotten one yet. So I decided to make one up around bonding curves, because while our final goal is to, of course, take this to help people that are protesting in the States right now, for instance. But we're not, it's going to take us time to get there. And so our expectations are to start with the communities that we're involved in. And look, we're sitting in a community right here. So I bet there's some really great public goods that the bonding curve space could use funding to produce. And let's talk about how we would use an augmented bonding curve to fund public goods within the bonding curve space. So the first step, of course, is to find the community stewards. Commons, which is what we call our augmented bonding curve DAO, and it is a community. And all communities start with a small group of people that get together to make a change, and at least within the commons space. And so if it's going to be a bonding curve commons, this group of friends will need to be respected leaders within the community. And they're going to hold the commons identity. They're going to be the ones that need to really explicitly state what is the value you intend to create. Is this bonding curve commons just a tool for all the large crypto ICO organizations to kind of like collaborate and get some CAD designs for what they're trying to build? Or is the goal of this bonding curve commons to bring a revolution in economics to all of society and change the world economies? These are the things, this kind of scope is very important to have everyone who's participating aligned around. As Paul said in his talk, it's really hard to just kind of come in with tech and expect everything to work out. Here's these cool tools, guys. We just made them for you. Let's do cool stuff. What do you want to do? No, it doesn't work like that. You have to figure out what you want to do first. And the people who are actually going to, who are experts in the bonding curves need to be the ones designing the bonding curve commons and saying what the goals are, saying what the values are, saying the vision, and figuring out how are we going to evolve with the community. If our morals change, how do we change our constitution? And having all of these things written down, and what is, explicitly stating what the value is that they're creating this economy around. And this what we call the cultural build is going to take a long time. It's not, we're talking about building economies here, this idea of just DAO it is not going to work. We need to, it hasn't worked so far. I think it's great for prototyping and experimenting, but if you actually want to make a change, you need to put in the cultural work. So once you have all of the purpose of the commons stated, of the bonding curve commons, then you actually need to create some roadmaps and just do some project management, right? There's the legal requirements, as Paul talked about. These are very interesting and a lot of work. The technical requirements, of course, maybe do some CAD modeling. The social requirements, the financial requirements to pull this all off, getting those roadmaps and aligning them together, while also making sure that you're actually building the commons and following the best practices that we know today from the social science research, mostly from Eleanor Ostrom, but also David Bollier and Michelle Bowens and many other leading or thought leaders out there. And so, okay, you have this plan, you have this roadmap, you have the vision. That's great, but you need to kind of share it with the world, like go a circle outside. So the community stewards are generally putting this all together for the bonding curve commons, but then they actually need to go talk to, talk to Zargham, talk to Simon, talk to Paul. I guess I put all their pictures in the first picture, but talk to the people who are that one circle out that you want to be involved in this thing, and get some feedback. Figure out if what you're building and what you're proposing and the value that you want to produce is actually going to be appreciated by those guys. Okay, so once you have the people and the actual cultural plan, then you can start recruiting the people who are going to fund this thing. So an augmented bonding curve is actually generally expecting a input of capital. This capital is most likely going to be a stable token like DAI. That's how Molecule used it, and it's probably the most simple use case. Of course, it can be some kind of like labor token, like source cred grain, or there's other experiments that you could use. But in general, you need people to kickstart this thing that actually have money and want to see the value that your community is going to produce actually exist. And these are what we call hatchers. And the hatchers will come in because they care about the system. And it's important that you are selective with your hatchers. Because if you choose, because the hatchers, while they are generously providing seed capital, they do that for a reason. They do that because they want to help steer this community. And they do that by getting governance tokens. And if you let people who are more profit-driven than value-driven into your initialization of the augmented bonding curve, it's likely that you're going to end up with a shit coin. And you don't want that. You want to end up with a really good system that's going to produce the value that you want to create, not just try to make money. So, okay, now you have all the people now and the plan. Now you got to go out another circle socially. You have to go tell the world about your plan. Tell them, hey, this is what we're doing. It's just about to start. Get kind of the hype cycle up so that people know that this economy is about to be kickstarted. But also, you want to find people who want to do work for this community. One cool thing about the augmented bonding curve is that in a way, it's a circular economy. The people, the hatchers that are putting money in, they can actually use the money that they put in to fund the projects that they want to do. They can fund themselves. And that's actually very preferable. But it's not, you don't want it to be just a closed circular economy. You want it to be an open, growing circular economy. So while you might have some projects that you want to fund, it's better to have competition of those projects. So if you can publish your plan, then more people can come in and join the party. Okay, so let's talk about finally where we get to more of the technical implementation. But it's worth focusing on the cultural. I know that we're all kind of like tech nerds, but we got to remember these are socioeconomic systems. So while we talk about the tech all the time, culture is most important. But now that we're actually going to launch a bonding curve, we start these with what we call hatches. The hatch is, well, I'll talk about what I'll go a little bit deeper into this right now. So the first thing is the hatchers, finding the people that are willing to put money in. When they put those funds in, those funds are split between two pools. The reserve, which as you heard before, it backs the bonding curve, and in our case actually backs the value of the bonding curve commons tokens, and is really effectively the reserve of the bonding curve economy. And then there's the funding pool. The funding pool is what is used to actually incentivize labor and to do work. This is a donation. The funding pool is where the donations go. So the hatchers need to be very generous. In this case, during the cultural build, the bonding curve commons decided to send 60% of the hatch to the reserve and 40% of the hatch funds to the funding pool. So effectively, 40% of the hatchers' money that they raised was a donation to the bonding curve commons. And they did this because they, in return, get really cheap bonding curve tokens. But those bonding curve tokens, because of slippage, they need to be vested. They need to be locked because, well, I'll show you in this next slide. when you actually do if there's one thing to know about bonding curves, it's always best to be the first person to buy. And this is just almost a law of bonding curves, because the bonding curve price in general will always be going up as the collateral pool grows, as the reserve grows. So when you bulk buy at the beginning, you can kind of average that advantage out so that you get a lot of people put money in. In this case, they put in $500,000 DAI, and they bought tokens at 10 cents. So 5 million tokens were created. And, but those tokens are only backed, those 5 million tokens are only backed by 300K in the reserve. So now these 5 million tokens are effectively backed by 6 cents. Each token is backed by 6 cents. But when the token goes to market after the hatch, when the bonding curve is open for everyone to interact with, the price of the token is 20 cents. So for the hatchers, they have kind of this dual price in their mind. They know that their vested tokens are only worth 6 cents. If the bonding curve commons completely fails and they just end up selling all of their tokens as they become vested, 300K will be able to come out of the reserve, and that's 6 cents per token. But the open price and the price that everyone gets to see is 20 cents. Now this is very motivating. This is due to the slippage in the design of the bonding curve, and because their tokens are locked, they kind of have this carrot that they're chasing, the hatchers of the bonding curve, that they need to develop real value with the system that they started. And the way they develop the value is by spending the funding pool diligently, that they actually, now they have skin in the game. If they do a good job at spending the donations that they raise together, then they will undoubtedly attract other people that want to be part of this community and act almost as a bonding curve commons impact investment. And so they need to make decisions, good decisions, that will support the growth of this community. And also, and the best way to do that, of course, is to have the impact that you said you would have, to follow your values and achieve your mission. And that would be by funding open source bonding curve projects. And one thing I want to mention here as kind of an aside is it's very important with our in the common stack design that you don't just send DAI to the projects that are being funded. You actually always want to, you can use the DAI as kind of a stable escrow. But when the open source bonding curve project wants to actually collect the payment, that DAI goes back into the bonding curve, into the reserve, and creates bonding curve tokens, bonding curve commons tokens, and those are what pay the people doing work for the commons. And this is great for 2 reasons. Number one, you always want to use your own currency, and that allows money to kind of stay in your system and create a circular economy. And number 2, these are the people doing work. These are the people on the ground. You want them to have an easy way to participate. And this is a way that you can allow labor to create governance and governance power within the system. So the reason that it's very easy to start growing once you have this system is that in our most basic design, when people want to join, at first, it's very clear that it's an easy decision, because in the end, when they put in 100 DAI during the open phase to join the bonding curve commons, they receive 100 DAI worth of bonding curve tokens. And when they do that, the price goes up because of the bonding curve, the design. And they're growing the internal economy. So at no cost to them, they are seemingly no cost to them at this stage, they are increasing the value of the bonding curve commons. And so they'll do this if the bonding curve commons does a good job. and they can see it as an impact investment. This is much better for a granting organization to do this than it is to just give away their funds. It's effectively a no-loss donation. But you, of course, need a way to sustain the growth of the funding pool so you can continue, so the bonding curve commons can continue to do good work. And this is where we implement what we call an exit tribute. And in the exit tribute, when people leave, you actually, and they burn their tokens into the bonding curve and release the die. Even though when they burn 100 die worth of bonding curve tokens, 100 die is actually released from the reserve. In the exit tribute, we will take, for example, 20% and put it in the funding pool. And then the person who's exiting gets 80 die back. And this is a pretty steep exit tribute. And what this does is this aligns incentives so that, as Jeff mentioned, you know, if people are doing actions that don't really serve the commons, they decide to take some profits. Maybe they bought commons tokens in the hatch and they want to, you know, they did good work to grow the community. So they want to sell their tokens and take a profit. That's great. They should be able to do that. But at the same time, we want to take that as an opportunity to grow the funding pool. Now, this is just one of endless number of ways to grow the funding pool. And really, you know, bonding curves are up to you. This is your opportunity to design whatever system you want. And the community stewards would do this, and they get to have the power. It's like a Bob Ross painting. And you don't have to follow what Bob Ross says. I just need to grow a fro. And then one day I can be like Bob. That's the show. We have so many links here. Jeff put up some of them too. We have a really great community, and we would love all of you guys to join. One of the important things that we talk about in the Common Stack is the cultural build. And to me, that means that we need people like you guys in this call to really put yourselves out there to be part of future communities that want to implement these systems. So one of our components is the Trusted Seed, and this is the group of token engineering experts and commons experts and really pro-social altruistic people that can be, you know, kind of like plants in future commons communities and be part of the hatches to make sure that these early adopters of this kind of stuff have people that they can rely on for good information. So if you want to be part of our mission and part of our community, please consider applying at commonstack.org/apply. Okay, thank you guys.
Griff, in the meantime, I'd have a question. So what are the next steps for the Common Stack, and how long is it going to take before this becomes a reality?
Well, you know, we're doing our own cultural build right now. We have finally, I feel like we've finally got enough people in the Trusted Seed to start really building their system. Hi, Sim. Sorry. Hi. There's a real world over here. Sometimes we forget, right? So our goal is now to start with an MVP Commons. This is what we want to do because when we started the Common Stack, we thought we would kind of go really fast and launch the Commons, you know, raise a bunch of money and start building this stuff. But we found that it was a lot harder to do that, and especially learning lessons like Molecule did about what needs to be done, the groundwork that really needs to be done on the social side. We have instead really, you know, gone slower. And now, look, the world is catching up with us. People are implementing our ideas before we can. So we're really excited about taking the tools that exist today and really try to do a commons, like a prototype commons.
Awesome. Thank you. Let's see if there is another question here. Is Common Stack sticking to developing on ETH using Dime, or are there other chains you're interested in?
So we have a very interesting development approach. Our strategy, and this is almost controversial sometimes, we don't want a dev team. I know that sounds crazy, but I've seen what's happened in other communities around like kind of getting entrenched in having a monopoly over a code base. We are going to create a monopoly on a code base, but actually it's block science that'll create the monopoly on the code base. We want to create really good designs for these systems that can be applied on any blockchain. We don't care. It's not, the point isn't to bring value to Ethereum or to bring value to Bitcoin. The point is to to support altruistic communities that want to create sustainable value. And whatever tools work, you know, for us, the focus is the design. So yeah, actually, Ethereum is probably the place to start. I like XDAI as a sidechain to build on. OneHive, I don't know if they've announced it. I don't know, but they're going to move Aragon to XDAI if it's not there already. So I'm very excited to start playing there where gas is cheap and we can use all the tools that they already have with a stable currency that people have access to. And it makes a lot of sense to start with Ethereum because it's easy. But when we do these big builds that we have planned, multiple iterations with different focuses on different layers, I hope that we'll actually kind of do one on each different chain and give a variety of code bases so that we have multiple teams with multiple expertise in using these systems in different environments. And then it can be a competition to see which ones are best.
Awesome. Thank you, Griff. So let's move on to the next talk. I'd like to introduce Shruti Appiah. She's a research scientist with formal complex systems engineering education. And she really is a pioneer in computational engineering of cryptoeconomic systems. She was a founder of Consensus Labs, I think, which is a venture studio. She's been a 30 under 30, and she's currently working on a really exciting system design that she's gonna speak about today, which is including a bonding curve, which is risk adjustable. Shruti, we're looking forward to your presentation.
Sounds great. All right, I will share my screen. I hope you all can see it.
Yeah.
Sweet. So thanks for the intro, Jeff. Jonathan, that was very helpful because I do have a slide out here. Oh, what is going on here? Right. No, I do not want to do this. Oh, there we go. All right. Okay, so today I'm going to be talking about risk-adjusted bonding curves. So this is a slight variation on the traditional bonding curve, and we will be exploring the differences and the contrast between the traditional bonding curve to the risk-adjusted bonding curve, which we're exploring for developing social impact bonds. So let's move on to the next slide. All right, so I think that Jonathan did a really good intro for me, so I will skip this slide. And then we'll do a little bit of conceptual review of what's going on with the traditional bonding curve and how it's designed with regards to configuration spaces and as well as economic games as estimators. So a lot of these concepts are actually applied in the bonding curve that Griff as well as Jeff talked about. And it's also applied in this particular variation. So this is a concept from robotics engineering and systems engineering about configuration spaces where you want to, you have a system and the system has a lot of states. And in order to deal with all of those states and do computations on those states, you typically want to make that space a little bit smaller so that that smaller space actually describes the states of the system that you care about and that are relevant to your system design. So in order to do that, what we do is that we impose constraints on the general state space. And then once we impose those constraints, we get configuration spaces. So these constraints are typically in the form of conservation functions. And I think Jeff also really did a very good job in describing as to what the conservation functions can be, and these are typically simply energy conservation functions such as the Lyapunov function, as well as several functions that we see in Newton's laws, as well as Kirchhoff's laws, etc. And now we have these conservation functions that are applied to bonding curves. So once we impose those conservation functions, we obtain a configuration space which is much smaller and of much lower dimension than the general state space. So once we do have that, we also need to be able to get certain information from the system that we don't have inside of, right? So, and this information we typically classify as private information. So if you think of all of us as individuals, we all hold private thoughts and private beliefs of what certain things of the system should be. So for example, if you have a system where there is a notion of price, right, such as a token bonding curve system, the price that you think or how you value the token is only an information that's in your head if you don't share it with anyone else, right? And so in order to extract that information from all of the agents, what we do is we use an estimator. So an estimator basically takes inputs of the agent's actions, and the inputs act as signals to the estimator, and then the estimator processes those signals to produce a system estimate of certain state variable. And that state variable can be something like price, or it can be something like alpha, which is what we will explore further. So let's talk a little bit about bonding curves and what I'm referring to here. So I want this to be a comprehensive presentation, right? So bonding curve is basically a mechanism to distribute. It's also a non-negative market maker, and these are two that are typically bonding curves actions that can be performed by agents. So they can either buy tokens or sell tokens.
Shruti, can I quickly interrupt? I'm having audio problems here. I'm not sure if that's from your microphone. Could somebody, same here, okay. Maybe there's a issue with the connectivity of your microphone, Shruti.
Oh, that's unfortunate.
Now it's perfect.
Let me.
I don't know, you changed something. Now it's perfect.
Was it a physical interruption or?
That's a good question.
All right.
Yeah, it's good now. Please go ahead. Sorry for interrupting.
Okay. I'll do it this way. All right. So in typical bonding curves, you have buy and sell functions, and those will either mint tokens or burn tokens. And however, a shortcoming in these traditional bonding curve for certain application or use cases is that these bonding curves have fixed a priori assumptions, meaning that once you start the bonding curve, there are certain things about the state variables that you aren't able to change. So especially in the use case that we're going to talk about today, which is that of a social impact bond, and the impact bond being a bond which is used as a debt instrument to fund social impact projects, which are dependent on the outcome of the project. In those kinds of cases, the risk factor or the external factors that contribute to risk or the success of or the likelihood of success of the project is extremely important to consider while the project is during execution. So the reason why we want to incorporate dynamic state variables is because of the fact that we want to account for risk and account for external factors while a project is during execution. So most bonding curves are static, so we will explore dynamic bonding curves in this presentation. So also, let's talk a little bit more about the risks or the shortcomings of static bonding curves. So since they have fixed a priori assumptions, they aren't able to incorporate risk or certain external factors during their execution, which is during their live or dynamic phase. And as a result of that, tokens may get misallocated, and risk sometimes will accumulate non-linearly if that's the way the relationship is. And as a result of that, there can be either systemic collapse or investors get poor ROI. So the former one, which is that investors get poor ROI, is usually the outcome of this. And systemic collapses still can happen, technically speaking, when the risk is accumulating non-linearly. So during closeout, which is when the entire project is completed, you will often see one of these two outcomes if you're going to be using static bonding curves in conjunction with a social impact project or a social impact bond that has a ton of external risk factors, and all of those kinds of relationships are very strong there. So what we can do instead is we can continuously estimate the likelihood of the bond's success given all of the external factors that we find out about during its execution. So what we have is that there is a data stream, which is that of external factors and risk. And we aren't able to capture any of the information that's in that data stream with a static bonding curve. But with this type of a bonding curve, we are able to capture that information, and we can dynamically adjust the bonding curve to those external outputs or external inputs. And then we have this risk-adjusted bonding curve. So you have this bonding curve that essentially adapts itself to the environment. So let's see how we model this. So what we did first, so this is some work that I did with my team at Block Science, and what we're essentially doing is we're going to be modeling the system, and we have done this in order to eventually write simulations and build a CAD model, as well as write experiments and make simulations so that we can validate certain assumptions about our project. So what we did here, the first step, is to describe the system as a finite state machine. And so each phase of this project is considered as a state in the system. And that state has an input, an output, as well as a state transition into the next state. And then the next thing that we did is that we had in this project, it was a very large space of different roles that were playing, that were part of the system. So this is a social impact impact bond. As a result of that, there was tons of service providers, there were tons of participants, and tons of people that had different roles, right? So what we did in order to deal with all of those nuances is we classified all of them into different agent classes. And the way we classified them into agent classes is by classifying them based on the kinds of mechanisms that they participate in, as well as the kinds of actions they're allowed to take. So then we arrived at these 4 agent classes that are in these different colored circles here. So the main ones that we want to really be looking at here are traders, as well as claim and dispute assurers, as well as outcome players. So what we did also was that since we were able to classify all of the roles into agent classes, with those agent classes came certain operational requirements. So operational requirements, if you think of it as in this context, is basically just certain requirements that are imposed in the system, which disallow certain agents to partake in certain activities or do certain actions. So they define kind of the legal set or the legal set of permissible actions that an agent can take. So as a result of that, we arrived at the action space. So the action space is a much smaller space, which consists of all of the permissible actions that the agents can take. And then the next thing that we did also was this was constrain the general state space as well. And as a result of that, we arrived at a much smaller configuration space. So now already by doing these 2 steps, which is to constrain the action space as well as constraining the general state space, we already have like decreased the dimensionality of a system by a lot. And now we have a much easier system to deal with. So let's talk about the mechanisms. So in this particular system, we have 2 interrupting mechanisms, one of a bonding curve, and then the second of a prediction market. So the bonding curve acts as a traditional bonding curve, and it has the 2 usual bonding curve functions, which is that of bond to mint and burn to withdraw. And these are the actions that any of the agents can take. And then the prediction market, though, has these 2 actions called a test positive and a test negative, which is basically the agent's way of saying whether a project or a bond would be successful or not. So when they are test positive, they're basically voting in favor of the bond being successful. And if they are test negative, they believe that they basically are signaling that they believe that the bond may not be successful. And so each of this is associated with a certain change in where the supply tokens go. So the supply tokens will either go to a bucket of S1 tokens, so they get bonded to S1, which is the bucket of supply tokens that are dedicated to positive attestations, or they will go to S0. And then so we have these 2 different mechanisms that are operating with each other, right? So how do we introduce the notion of invariance here? So the way we do that is we discovered in that in our system that the invariants are actually only invariant on one of these mechanisms at a time. So for example, we have this V invariant, which is only invariant on the bond to burn mechanism, but the attestation mechanism, so whenever an agent does an attestation action, it would change V. So it's not conserved under the attestation mechanism. And similarly, in the attestation mechanism, we have an invariant I, which doesn't get conserved on the bond and burn mechanism. So whenever an agent wants to bond or burn tokens, the I invariant would change. So this is the nice thing about hybrid systems, is that while they are independent mechanisms, the bonding curve mechanism as well as the prediction market mechanism, they're interoperating with each other even though they are independent. So the changes in one mechanism can affect the state variables that will have a role in the other mechanism as well. So you can see that when a bonding curve or a bond action is done, then there will be no change in the invariant V or kappa, which is the curvature of the bonding curve. And then V is also conserved, and then there's a change in all of these state variables. And so this entire side represents just the traditional bonding curve working. And then this entire side represents just the traditional prediction market working. However, when they interoperate with each other, then you can see that these are only the changes that they would induce on the other mechanism, which is really nice and simple. And so now we are able to digest essentially how two mechanisms can work with each other. And so the crux of this project is actually estimating risk and being able to utilize this risk parameter, which is called alpha, in order to determine the payouts that the project will receive or the agents will receive at the end of the project. So alpha, which is the risk parameter, it determines the likelihood of success of a bond. And so we initialize it to some value. Let's say we initialize it to 0.5, right? So 0.5 would indicate that the project is equally likely to succeed or to fail. And then whenever an agent would attest positively, that means they attest in favor of the project succeeding, then the alpha would increase. And then whenever the agent any other agent would attest negatively, that means they believe that the alpha, their private alpha is actually lesser than the alpha of the system, then the alpha of the system will go down a little bit. So at the end of the day, we will at the end of the system, we will arrive at an alpha, which is the final alpha, which will be a compilation of all of the agent actions. So the game acts as an estimator of alpha. So ultimately, all the agents have a private belief, and this private belief, whenever they do take an attestation action, that action acts as a signal for their private alpha. And then once we have that action, which is the signal which is revealed to the system, then we will be able to use that in the estimator, and then we can finally get a alpha estimate, which acts as the system alpha. So that way we're able to get private information and make use of that private information to make an estimate or an estimate of the system. So we also make an update on alpha. So if you remember the previous diagram that we saw here, how does alpha get updated here? And the way we do that is by using a Markov chain update process and a convex combination of the current alpha as well as the realized alpha. And the way we do this is because the way we use the Markov chain is because of the fact that we don't want the alpha to change so significantly just based on a single agent's action. And the reason why we use a convex combination is so we can maintain that alpha between 0 and 1, which is the domain of the alpha that we have defined. So here we get the next state alpha based on the current state alpha, as well as the realized alpha, which is essentially the alpha that the agent gets when they are taking the attestation action. So then we arrive at the update of the alpha. And so this is how we account for risk in a short sense of the system. And this is how we would get private information and are able to use private information in order to make certain estimations about system level state variables. And with that, I will take questions now. And you can also check out all of our work. We have posted it on BlockScience/Interchain Foundation. And you can also reach out to me if you have any more questions offline, if you would like. And yeah, so stay virtual.
Thank you, Shruti. That was awesome. So unfortunately, we don't have time for questions right now, but please do reach out to Shruti. All of that work that you've just been describing is open source, right? So people can really check that out. I think there was you dropped a lot of awesome stuff there. I think people need a little bit to digest that. So that's all available on GitHub, is it?
Yep, it's available here on the BlockScience/Interchain Foundation. So a lot of the work that I presented today does have to do with further explorations that we have done, and we will be posting that soon. But all of the work that I presented on the former part of the presentation, that's all available on the GitHub link right here. And that will encompass all of the engineering requirements and the system requirements that we have done so far.
Perfect, thank you. And with that, we'd move on to Shaun Conway, who is going to give the project context that implements that bonding curve design. Shaun is the co-founder, is the founder of ICSO, and he started his career as a medical doctor, actually. And he was involved in system design and data-driven responses to global health challenges. And for the last 10 years, he's been on a mission to build a digital immune system for humanity. I had to read that because it's so awesome. Shaun, we're looking forward to your presentation.
Fantastic. Thanks very much, Jonathan. So it's really great to be talking to you in the same panel as people who have been building on these ideas for some years. And I remember meeting up with Simon in 2014 and working with Paul over the past couple of years, and then finally sort of coming to this engineering work that's being done with Block Science. It's really a realization of some ideas that are really about how do we deal with complex systems challenges. And so what I'd like to talk about today is some really practical use case of these mechanisms within the context of development finance, and specifically to kind of talk through kind of how this overcomes some of the constraints of analog systems moving into the digitization of those systems, and then kind of where we're going with what we can call cyber physical systems. And so hopefully this kind of puts into context everything we've heard about tonight in the context of real world complex systems. And what I'm going to talk about specifically is the implementation within the context of primary education in India. And so we have a project we're doing together with UBS Optimus Foundation and UBS Bank, which is a 4-year project to do research and development around how to really change the game in terms of development finance for social impact and environmental impact as well. So when we're looking at this from a systems perspective, we're really trying to achieve some system level goals. And so, I call this kind of seeking alpha. Essentially, we're trying to reduce these risks that systems have. And in reducing the risks, we're trying to increase the impacts that can be achieved, the capital returns that can be realized by investors, and then increasing the positive externalities whilst ensuring that the negative externalities are decreased and making sure that the projects actually get implemented. So these kind of 5 system level goals are generic, but if we look at them in the context of this education initiative, the impact specifically that the development impact bond that's currently underway is looking to have is to improve the literacy and numeracy of at least 200,000 school children. So this is currently funded and it's currently being implemented. It's a drop in the ocean compared to the huge need to transform educational needs and quality education within a country like India. The second part of this is that investors are putting in capital and want to get some capital returns back on this, and want to do it in a way that their capital is preserved and the risk is reduced. And so we want to kind of create this promise of something like a 10% annual rate of return. The positive externalities in this is that the system should strengthen the educational system overall. It shouldn't just be an initiative which is narrowly focused and that just kind of funds a few people to do a few things. This should actually contribute to system strengthening. And I need to somehow reduce my, I can't see my screen properly, but okay, so it needs to also decrease the negative externalities, such as the dependency that we often see with these kind of financing initiatives on external agencies. So we want to bring about much greater autonomy and ability to for people to take care of themselves. And then finally, not having dropouts from the program. So this is how a results-based finance mechanism works in a traditional finance context. I mean, really, these are some very generic concepts that risk investors would introduce the capital, which is working capital that gets utilized by the service providers, but with some promise that the outputs of the service providers, or actually the outcomes, so the impacts that are going to be achieved, will be purchased or funded by some outcome funders. And outcome funders can be governments, they can be development finance institutions, they can be sort of really anyone who's interested in the results of what's going to be funded. And in this process, in order to repay the investors, there's an independent evaluation process, and that will then verify whether these outcomes have been met. And if they have, that triggers repayments. And if it doesn't, then it triggers losses. So in a traditional finance sense, there's a configuration that needs to happen. You need to set up this instrument, you need to set up the projects, and you need to issue the bond as an instrument. And so, you know, a number of the challenges that you have in this initialization are actually not uncommon to the challenges that we have, even if we're trying to do this in a sort of kind of new economy, crypto economic sort of sense. But specifically in traditional finance, we've got the problem that you need to form all the capital upfront. So if you're going to implement this project, educating 200,000 school children over four years, you need tens of millions of dollars, and you're not going to start that project until you've actually got the capital in the door, which means convincing investors that they should invest. And that means finding like-minded investors with similar tolerance to risk and so on. And so you kind of have this startup kind of problem. Also, you're trying to estimate the risks, so the cost of capital upfront, ex ante, which is really just, it's a bit of a joke. I mean, most of these projects and programs are completely unpredictable. They're all startups. And so trying to estimate what the capital is going to cost and factor in risk ex ante is really just a joke. And then there's the whole process of commissioning the services, contracting counterparties. How do you calculate these outcomes? What's the methodologies, etc.? And then somebody has to carry the overhead of this whole system. And so whilst these results-based financing mechanisms are kind of sexy in their sort of ideology, in their practical implementation, they're actually really difficult to do. And this development impact bond for education in India is the last one that's been done for a social impact program. And it's taken years to design, and it's complicated and maybe too big to fail and so on. And so in these systems, we tend to find that the information flows through the systems and even the financing mechanisms are what I kind of would call analog. And that means they're low definition. You know, think of kind of analog televisions and, you know, all that kind of quaint stuff that we grew up with. And so the data is low resolution, and I'll explain it a little bit. I think it'll become clearer as I come through this. It's low fidelity. So on the right-hand side there, you've got a picture of some dots and a grid. So imagine this is 200,000 school children over 3 states in India, hundreds of schools, many of them very, very remote. And so really collecting information and trying to resolve that information to understand what's going on, to understand what the risks are, is extremely challenging. And so generally the system is information poor because of the way that the information is collected. And because it's information poor, the risks are quite relatively unquantified, and often the kind of the information that's coming through is not really well correlated with reality. And so, you know, I've been out there into some of these project sites. This is just in West Delhi, and here the children are completing some independent assessment exams, which is the basis on which they get evaluated for whether they've improved their education or not. And this is really analog and low definition. And so what the project does is you have a baseline measurement using those methods, paper-based tests and so on. And then there's a follow-up sort of at the end of each year. And so at the end of year one, you get this average, which is based on randomized sampling and sort of very sparse data. And so it's kind of an impression that, yes, this has improved. It costs a lot of money to actually get this information because you're sending people out to go and invigilate exams and so on, and then collecting all the papers and shipping them or flying them off to somewhere where they will get inputted and so on. And so this is not really a sort of very valuable exercise, but it's the whole basis for this results-based financing mechanism. And so what we've looked at to improve this, to improve the effectiveness and the efficiency, is to bring in digital innovation. So improve the resolution, improve the fidelity, collect more information so it's more rich. You're able to then quantify the risks, and you're able to have a much greater correlation with reality. And on the right-hand side there, you've got a data graph. So you've got linked data. If you collect the data in the right kind of ways. And so with ICSO, we've been working on protocols around what I call high definition data. So this is using linked data, using semantic web, and using verifiable credentials, which hash the data. You can timestamp it, put it into sequential graphs, and everything is signed. And so there's a lot of fidelity in it. There's a lot of resolution because of the resolution around identifiers and so on. So there are protocols, data protocols, that enable us to get this really, really much higher definition data. And so here in the same schools, what we did was we gave the children tablets and captured the data directly on the tablets. And the whole mechanism around this enables for much greater data collection, much more accurate, much more sort of high fidelity, and you can bring in all kinds of designs in terms of like good comp sci practices around reducing attack vectors and so on. It's like randomizing the test questions, and putting various other limitations on this so that you don't get cheating and you don't get gaming of the system. And so feeding this into a blockchain-based platform, we can now create the stateful data, which creates these records over time, which enables us to now build economy on top of that and build mechanisms on top of that. And I think that this is like a really key concept in mechanism design, in crypto economics, and in bonding curves, is that if you can build these systems on stateful data, you're able to build economy that is able to represent a state of what is today, the state of the world, and then incentivize the achievement of future states. And this is particularly important in the sustainable development and kind of impact use cases. And so now, this is really conceptual, but now we can really kind of get a high definition, full color picture, because we're able to collect data right down at the individual level. So individual children, we're able to get everybody to be tested, and we're able to feed that in using good data and using digital signals, and we can feed that in to now create an integral measure of what has happened over the year, rather than just some sort of abstracted average. So in terms of signal processing, the next level on this is that we're implementing a pilot together with an NGO called Chimple, and they've developed tablet-based learning tools which collect data as the children are interacting with the tool, and as they're learning, they're achieving different levels of achievement. And so that is sending through the information. And so now we've got the prospect to collect data real time, which feeds into our understanding of how this is progressing towards those future states. So the children want to get to a point of provable literacy and numeracy, and along the way we can see the levels of the game that they're kind of getting to. And that's providing us with a signal that can come into the system. Now, how we link this signal to the financing is we're the bonding curves come in. But I just want to make a mention here of the value that gets created when we put in place these kind of systems that are data rich and that are incentivized. And so I like this kind of rule of thumb thing here, P functions. So when we start to have good data that we can perform operations on, we can use functionally, we're able to not only just prove that the claims are true or not, but we can also use this to make predictions. And so this alpha is a good example of the prediction. So we can predict the risk. We can predict whether this program is actually going to produce the results that we wanted to achieve. And that prediction can happen at the level of the system, or it can happen right down at the level of the individual child. So we can predict, is this child going to meet the grades and so on? If not, how do we create an information feedback loop which personalizes the curriculum whilst ensuring that you have like a protection against privacy infringement and a whole range of other sort of threats that might occur. And you can proactively then use the data to prevent learning risks, such as the risk of failure and so on, and prescribe specific measures such as remedial support and so on. So this is obviously all in the context of this education program, but it's generalizable to any system that is built on good data. So now the third sort of evolution in these systems designs is cyber-physical systems. So we're moving from analog to digital to cyber-physical. So from low definition to high definition to digital twins. Okay, and so here we've got not only the sort of resolution of the data, but also how that data gets fed into a live system that provides feedback loops, which enables us to make decisions, adapt, and so on. And we can then utilize that feedback to do trusted execution. So in a sort of robotics engineering kind of analogy, we can put in place controllers which ensure that you can only operate within certain parameters that are safe. And as this information feeds through, it builds intelligence in the system. More data creates more intelligence. And if we use the data with machine learning, but we also bring human inputs into this, as Shruti was mentioning, bringing private beliefs in, for instance, this enables us to become much more intelligent. And then we can attenuate the risks by this sensing and responding set of mechanisms. And this much more merges with reality compared to that abstraction that we see with going out and handing out some test papers and getting a few children to answer test results. We're really merging reality with humans in the loop and economy in the loop. And so the economy in the loop part, which is where we get to bonding curves, firstly, I think really in an exciting way implements this principle that prices incorporate a whole lot of information that we can't even necessarily measure. So we've got private beliefs, we've got various data feeds and so on, but ultimately price, according to Friedrich Hayek, gives us this communication of information that is more than the sum of the parts in a sense. And then to quote the Dr. Zargham, and then we get into economic games as estimators. So we've got price, but we've also got like a gaming on that price. We've got an interaction with that price. And so now we start to get a lot more information. All right, so we looked at the configuration space from a traditional finance or conventional impact bond perspective. Now we've got a crypto economic design. So again, a configuration space. And so within that space, we can say, all right, this is the space that we're going to design and play the game in. And this is a state space. Okay, so we're able to build on stateful changes and records over time. And we're able to do that through both the state and also the space that state occupies. And so when we talk about space, for instance, fiscal space, so what is the budget? What are the financing parameters here? Then what is the economic space? How do we interact with those financial flows and the capital that's available and so on? So what are the economic mechanisms or game mechanisms? And then how do we generate that state? So what are the claims that are required in order to go from one state to the next? And how do we drive those state changes towards a future state which is has achieved what it was meant to achieve? So an alpha of 1. So that's defining an attainable future state and then making everything work so that we can get there. And then in the process of getting there, we need to have state transitions. So what triggers those payments? You know, when alpha is achieved, outcomes payment is paid. So we need to have some conditions and mechanisms for state transitions to happen. And then ultimately, how does this play into a bigger economy in terms of being able to leverage capital markets and play into new kinds of markets? Well, we need to have ways of transferring information about economic value, and tokenized outcomes are a really great way of doing this. You know, so yeah, so here we're kind of figuring out our best guess of the curve, and generally to demystify this. So if you ask anybody, kind of, what's your project going to look like? You say, well, it probably starts off a little bit slow, and then we pick up and we do quite well, and then towards the end it's a little bit difficult to kind of finishing everything off. And so this S-shaped curve with a bit of hand waving is pretty much what everyone would say the project looks like. And so we can get some reference ideas around what to expect, and then we can measure against that expected. And then we can configure things like the outcomes payment. So we can say, well, outcomes payer will pay back all the costs plus a coupon value. Let's say it's 10%. So we can configure all of this into the system, and then we can start to play the game. So this is my attempt to just try and represent what the game might look like. This is in anticipation of the nice CAD models that Block Science is busy building, which will have fantastic visualizations and everything. So yeah, so we've got the idea here. You started with this alpha of 0.5, 50-50 chance that this project is going to fail or succeed. And investment comes in the background. Didn't animate this, but in the background you've got claims coming in and you've got verifications happening, and so you're kind of building up towards the outcome, which is children becoming numerate, becoming literate, and so more money comes in into the bonding curve, and the alpha is changing. But maybe something happens in the course of this project where alpha suddenly dips down. So our signals that are coming in say, well, alpha is actually not has gone down because this project seems to be hitting a bit of a skiddy patch and is going to not maybe not achieve its outcomes. And so now you've got some investors who say, okay, we're actually going to move our position. We're going to move into the predicting that maybe this project's not going to work, and so they move their stake from in the prediction market from yes, this project is going to succeed to the no, this project's not going to succeed. And so we go on, and alpha, the project gets back on course, alpha increases, and we get to a point where alpha hits 1, and so the payout happens. And so now we have the stakeholders in the project getting their or in the bond getting their returns. How do we interface this with people who aren't interested in bonding curves and who just want to put money into a project and make sure that they get some money back and the project does good? Well, this is all in the interface design, and really what we've implemented here is something that looks pretty much like traditional finance. This doesn't look like an impact bond. You don't really need to know about impact bonds and so on. You just need to know that you're taking a share in the bond. You've got an investment. You can withdraw it. There's returns, etc. What's really exciting about these mechanisms is how they potentially enable a different set of dynamics around stakeholding. So these dynamics are both about humans in the loop, so I can explain this in a way that when I went out to the project in India, and it's a results-based project, and I spoke to agents on the ground, so the people who are actually educating the children. I said, you're part of this impact bonds project, and this has got some incentives in it, so if you guys do well, then everyone gets paid out. And they said, we really have no clue what those incentives are. We're just told by head office that we need to do a good job. I go to head office and I ask head office kind of what's the incentives in this? And they say, well, yeah, it's somewhere in a big contract that sits in the finance director's office. And so there's really not humans in the loop of that mechanism. So how do we bring everyone into this picture? So just as Griff was mentioning in his presentation, you can, for instance, implement a mechanism where people get paid in bond tokens. So they can either choose to take the bond tokens, or maybe depending on how you set it up, you could actually make that a condition of their implementation of this mechanism, so that you need to be paid in the bond tokens, which means you've got a stake in the outcome. By having a tokenized mechanism and having this kind of bonding curve mechanism, which is continuous and which allows for people to come in anywhere along wherever they feel comfortable in terms of their risk appreciation, and also in terms of like what they can afford and when they can come in, we create the potential that everyone can get staked into the game. Everyone is then incentivized to achieve the future state, and everyone is participating both to the formation of the capital as well as the allocation of the capital. And linking these kinds of mechanisms to governance mechanisms helps that process as well. So if you've actually got a stake, you can then participate and vote in governance proposal and so on. This really does change the game. And so we can also envisage this as being a decentralized investment committee that is making decisions about projects and ensuring that they succeed. So
Shaun, apologies to interrupt. We got to move on to the next session. Is there any way you can wrap this up in 1 or 2 slides and tell people where they can deep dive if they want to know more?
So
thanks.
So I think in terms of like the bottom line is if you wanted to really have scale, how do you implement 1,000 of these impact bonds or these alpha bonds? Well, the answer is you don't. You let them implement themselves. So this is really about creating autonomous, replicable mechanisms that are properly designed and engineered. And this is why the work that block science is doing is so important, so that they can operate out in the wild and people can actually set up their own bonds for their own education projects, for instance. So schools can actually set up their own bonds and implement that. And that's really the end of this, other than to say the applicability is really generalizable. We've got the Sustainable Development Goals, the 17 Sustainable Development Goals, as a sort of guiding framework in terms of like the scope of what's needed. But we can apply this debt-based financing mechanism to really any use case. And so where to look for more information, you can contact me on this email address or look at ixo.foundation. And yeah, there's a lot of resources available to kind of read about this and learn more.
Thank you, Shaun. So we are at the last session, and I'm very happy to announce that Dr. Zargham has joined us. So it feels a little bit like introducing a family member to the family because we kind of all know each other here. So Dr. Zargham holds a PhD in systems engineering, and he's worked at the University of Pennsylvania on optimization and control. He's the founder of Block Science, but he's also invented the CAD library that we've talked about in many of these talks. He's been in one way or the other involved in most of the projects that we've talked about today. So in essence, we could talk about a lot of things with him today. Why I thought this session at the end would be exciting though is because Block Science and Dr. Zargham work really at the intersection between sort of pure theoretical science and, you know, if you will, for me, like cryptoeconomics is more the scientific side, and then token engineering is kind of the applied science side, and Block Science and Dr. Zargham sit right in the middle. So I'm looking forward for perspectives on how the scientific world sees not only cryptoeconomic systems in general, but especially those using token bonding curves. We're looking forward, Zargham.
Awesome. Well, thank you very much for having me. I am going to share my desktop, and then I am going to go to play mode, maybe go to the beginning instead of the end of my talk. quick reverse preview for the things I want to talk about. Okay, so I'm going to talk about bonding curves, configuration spaces, and estimators. A lot of these concepts have come up in the various applications, but I'm also going to start with talking about how this relates to the sort of academic versus the applied, the application of these theories, as Jonathan mentioned. So I'm going to start with a quick note on, so my PhD was at Penn, technically in a robotics lab, and I worked on basically this kind of decentralized optimization over sort of private decision makers with private information type problems. There's a family of mathematical problems called like essentially distributed optimization, but in the formal sense, if you look at the mathematics of it, the individual agents are local and they have local information, and the coordination task is the essence of the optimization problem. And I was a member of the group of Ali Judbabai, who's the director of socio-technical systems at MIT now. And you can see from, I grabbed his page to kind of show you, this is the area of academia that I come from. And in particular, I'm here on the group alumni site, and here's a link to what my dissertation was. And what you'll notice is that despite the fact that these concepts have a lot in common with sort of crypto economics, there's zero crypto in this field. Like if you were to go through, you'd learn about learning in games, and you'd look at different types of privacy preserving computation and all sorts of cool stuff that's going on. But there's like almost a complete absence of the sort of crypto economic thinking. But there's a ton of overlaps in terms of the mathematical methods. And there's a long history of complex systems, cybernetics, multi-agent control that one could dive into. And you often hear me talking about these things. I'm not going to try to give a survey of all of that today. I'm going to focus on bonding curves, but just to give you a little like precedence, this is sort of how I got here, and it wasn't really through crypto. What's really interesting about this though is these are people, and this is a field that's drawn heavily on robotics, and as a result has a very real application flavor. It's not about theorizing about what an economy might do, it's about actually understanding the way decisions and estimates actually emerge in systems of many agents. And so I tend to fall immediately back on this particular subset, which is cyber-physical systems. And again, many of these topics were referred to, but in particular, I like to highlight the definition. A cyber-physical system is a mechanism that is controlled or monitored by computer-based algorithms, tightly integrated with the internet and its users. And although this concept was coined relatively recently, the actual application of it, the making of such things, actually extends further into the past. Basically, from the beginning of networking, not even just the internet, but the ability to sort of network computer systems, we started creating computer systems that webbed things together, that included the capacity for human inputs, human oversight, or even human behavior being monitored. We have this sort of great material from Berkeley that I always recommend people check out as a sort of foundation of applied complex systems engineering. And then we can talk specifically about economics. And the field of economics is broadly the study of coordination processes of both human and, in this case now, machine decision-making about how to allocate resources. And ultimately, there's not one concrete definition of economics in even the economics literature. So I cite a paper here that actually goes on an overview of all the different ways that economics is defined and the sort of various similarities and differences. And for our part, I think we can focus predominantly on the relationship between systems and agents. And for systems, we often look at the institutional economics and the way that we think about these higher order combinations of behavior and the structures of decision-making result in sort of entity level behaviors or entity level properties. And we generally refer to this as system level, but this is interrelated with the individual decision-making processes and the individual beliefs and the way that agents work. And if you look at the historical literature on computational social systems, computational social science, you'll see sort of bifurcation between a very system-centric view, which comes from the sort of Forrester tradition, and a very agent-centric view, which is the sort of ABM models that are very popular now. And what we find is that in practice, we actually need both of these things to reason effectively about these systems, because there's actual feedback between scales. And so this particular diagram is interpretation of a concept that's expressed in a paper called Micro, Meso, Macro, of which one of the authors is Jason Potts, who's very active in the sort of institutional economics of crypto. He's at RMIT. And I think that really important fact here is that we design some policies or some algorithms or decision-making rules that actually just give agents the set of actions they're allowed to take, much like Shruti discussed earlier. And that then agents make their own choices based on their own private signals about what to do. But the system level state sort of emerges from all those individual behaviors, interactions between agents and each other, interactions between agents and the sort of perceived state of the system. They can see either directly or indirectly the sort of nature of the system they're participating in, and that will influence their decisions. So we can't just have the system level view, and we can't just have the agent level view. And in fact, our algorithmic policy sort of design space is really related to pasting these two things together, and it's quite non-trivial. I recently tweeted that algorithmic policy is everything you don't understand about machine decision making combined with everything you don't understand about human decision making. And I think that that really holds true, and that our job in both crypto economics and token engineering is to both improve our understanding and then build things that leverage that understanding to help sort of people achieve ends, you know, that are for themselves, maybe not so much for the system. Or you could say that the system's behavior is, you know, something that's being kind of co-steered with the people rather than the system imposing on people. And in fact, the bonding curve is an example of a price discovery mechanism that helps us sort of, the bonding curve doesn't set the price, the bonding curve gives us rules about how the price is discovered as a function of the decisions of the individual agents. And this is a broad concept that I think really can be refined in the network science literature, and in particular, this sort of economics cross complexity science topic, where we're really looking at the way individual agents express their decisions and the way that the systems sort of aggregate that into system level properties. And again, if you think in the agent-based modeling framework, what you're talking about is the patterns that emerge from a set of local rules, but these individual decisions aren't in a completely blue ocean or green field environment. They're acting on something with some fundamental process models, whether it's no double spends or whether it's the bonding curve invariant, something about the algorithmic policy or rules that restricts the space of actions that you can take and defines the consequences of those actions is actually channeling the information from the individuals into this sort of system level behavior. So what we really want to do is understand how to take these theoretical models of complex systems and the real data and the real decisions of real individuals and fuse them into a practical system that helps us achieve, like, you know, some desired outcomes. And sometimes desired outcome itself is very tricky, because in a decentralized system, there isn't necessarily a unique global utility function that we can optimize for, but rather we have to abstract it some and say, you know, everyone has their own, you know, wants and needs and preferences and signals. And if everyone acts according to their own sort of private subgradient descent, what can we say about the trajectory or the direction of the system as a whole? And for that, we actually, like, at least I rely heavily on analogies to robotics, and in particular because they give us nice formal mathematical structures like this thing, the configuration space, for the set of things that can happen. Not the set of things that will happen, but rather the set of things that can happen. And this is super interesting in the case of a multi-agent system, because the multi-agent system has this property that everybody's doing stuff and it's all legal stuff, but whether or not you actually get the intended outcome is in the sense of a specific trajectory is really unclear. And so in this arm example, we can imagine that this arm has a set of configurations it can take. So it can't violate the sort of lengths of the lever arms or the angles where it can bend, but actually it can do all sorts of different movements. And if I gave you a controller to control it and you were the only one controlling it, you could probably get the hang of using it to do stuff like, you know, pick something up, move it, take a marble and put it in a bucket, or generally, you know, do stuff. Now, the real challenge arises when I give everyone on the call a controller to the same robot. The set of things or forms the robot can take is still restricted by the robot itself, but it's probably, at least initially, going to flail around because you're taking actions based on your observations of the arm and seeing where it is, thinking about where you want it to go, and then moving it according to, you know, your controller, which allows you to say, you know, bend it in a certain way. But if everyone's doing this at the same time, it's really unclear what kind of pattern is going to emerge. And in fact, in a way, accomplishing something meaningful could be done by functionally colluding to sort of agree external to the system to do something that we want to do. Or maybe it's just that we all do our own thing and the system is actually capable of sort of averaging that out into something meaningful. And this is kind of what we hope for with the price discovery mechanisms and also what we hope for with the sort of alpha discovery mechanisms, where we're not even making the assumption that people collude, we're making the assumption that people do things based on their own private signals, preferences, etc., and that the system has retained some critical properties for all sequences of actions, regardless of whether collusion was in place, regardless of what the underlying incentive that drove the action was. We're still mixing or fusing all of those individual signals into an aggregate system state, which is still guaranteed to be in the configuration space. So as long as the most important properties of the system are characterized in terms of the configuration space, we do have some sort of first order safety properties. And for the robotic arm example, one interesting fact is that, you know, medical robots often have physical restrictions on certain types of movements that are, you know, beyond just what the software can or can't do, that it will actually physically be unable to do certain things in an effort to make those safer, even in the case where the software has some sort of malfunction or issue. Sort of moving on, this is our formal characterization of the configuration space of the bonding curve. And I'm not going to read you this whole thing. The paper's available. And this is part of my ongoing academic work with the VU and the Interdisciplinary Research Institute for Cryptoeconomics, where we're really trying to take these robotics formalisms and sort of show that the bonding curves are actually an instance of this kind of thing. We're not saying that bonding curves are the only configuration spaces, but they work in a large part because they can be described using configuration spaces, and that the properties that we really care about in our real systems are manifest in these configuration spaces. So if we want to learn from the mechanisms that we have designed and that are starting to work in practice, what about them made them work, and how do we make other things, or how do we combine them into multiple mechanisms working together and retain some of the properties that the individual parts had. This is where we would use these concepts in robotics and systems engineering to define state spaces and configuration spaces and look at what is preserved under what conditions, and actually take that into our design and into our testing methodologies. So what you can see here is we've highlighted the relationship between the system level state and the agent level state, and the way in which these enforcing rules reduce the system space to a lower dimensional than the sort of raw dimension of the total number of states through these equality restrictions. Visually, this is generally presented in various forms of plot, but ultimately what you're seeing is a line that's a one dimension in a 2D space, or another characterization might look at it as a 2D thing in a 3D space where we're talking, or in a 4D space where we're talking about the supply of the reserve, but also the ratio of the supply to the reserve, and also the sort of areas under these things. So you can think of the tangent of this as one augmented state, and maybe the area under an action as another kind of augmented state. It does depend a little bit on how you want to represent it and what concepts you're dealing with, but the fundamental degrees of freedom in the system are actually only one. You're moving along a line. And when you start to compose with other mechanisms, you add more degrees of freedom. This same system, actually, this same 1 degree of freedom at the system level can be manifest at the agent level when you go to take an action. So the relationship between these two curves are the way the system level state mutates when an action is taken versus the way an agent's level state mutates when they take an action. And these are just different perspectives on the same action. One from the impact on the system states and one from the impact on the agent's states. And by building the relationship between those two things, we can take a very signal processing like view of this estimation process. So if there's some private signals and agents are taking action according to their own sort of local optimization problems, or even just intuitively acting, and we interpret that as, you know, having some preference or signal behind it, we can look at the way that this signal is aggregated through the process of transacting on a bonding curve. And the Economic Games as Estimators paper is an example of how this could be applied in the context of a bonding curve specifically. But again, this concept of estimating through observing the actions of agents that are modulated by a set of algorithmic policies is far more general than just price estimators with bonding curves, and can include things like the alpha estimator, which is in the family of prediction markets. You can think of it like estimating the odds. But what's very interesting about Shruti's work here is that we're not just looking at someone placing a bet. We're actually looking at economic incentives that account for the way in which the odds are updated by that bet. So it's a bit like your bookie updating the odds in real time after every bet to preserve a sort of indifference invariant that says every bet results in a new set of odds that make the next bet essentially a wash if you believe the odds are right. And that kind of feedback loop is the same kind of feedback loop that's present in this price estimator. And it's the kind of thing that we want to bring more generally into the idea of how do we gather information from individual actors. We do it through invariant functions, and by embedding the preservation of those invariants inside the policies or the economic mechanisms at play. So in the case of Economic Games as Estimators, paper I wrote with Chris Baruch and Jamshid Sharish, we did some CAD-CAD modeling to sort of show how this sort of tracking property or price estimation could resolve in with a random sort of martingale dynamic. So like basically random sequence of price preferences on agents and the way the spot price can actually sort of track that, that over time. And this is sort of going to hold true regardless of what we set as the sequence of price dynamics. So we're doing a sort of tracking or estimation problem demonstration and sort of show that these actually very rich and long-standing techniques in signal processing and optimization and dynamic optimization actually do stand up to the sort of, hey, we don't know what people think and why they think it, they just do stuff. We really want to treat those people as expressing information rather than judging them as being rational or irrational as a result of their actions' deviation from our expectations. So I'm going to probably try to wrap up, but first I wanted to make a comment about what happens when there's more than one mechanism or more than 1 degree of freedom. And most of you are familiar with the Uniswap application, and I think that it's a really good example of a sort of very basic multi-mechanism scenario, because the ability to swap versus the ability to add or remove liquidity are actually 2 different mechanisms. They each are one-dimensional movements. In the case of the add or remove liquidity, your sort of one dimension is the sort of area of the square, the invariant, this product of x1 and x2, and you're really forced to add or remove liquidity in a way that matches the current ratio. So this angle is preserved. So you're making the box bigger or smaller depending on whether you are removing liquidity or adding liquidity, but you are restricted to this diagonal line as in the left diagram. Whereas if you want to swap, you're actually preserving the area, but you're changing the angle. And what's really interesting about this to me is that it has a lot of like very similar feel mathematically to the idealized robot, which is called a unicycle. And a unicycle is basically a little model of a point that can turn So it sort of it faces a certain direction. So it has a direction, and it has an ability to change direction. So the angle changes, or it sort of accelerates or decelerates forward and backwards. And this is a very primitive representation of a set of admissible actions for moving a robot around a two-dimensional space. And you tend to learn how to control and manage it as part of a mechatronics or robotics intro class. And the fact that the Uniswap actually has very similar, like sort of angular plus sort of forward backward sort of mathematical relation actually really highlights the way that you know, an idealized market could be used to start to reason better about maybe a much larger family of markets that aren't necessarily implemented as Uniswaps, right? It's an idealized market. And in fact, here I've even removed the fees, which we know would result in changes in the area when we would move along the swap. So it would be a slightly richer coupling because a swap on the right side mechanism will actually still increment the area slightly because of the small fees baked into an instance of Uniswap. And the value of those fees functionally accrues to the pool token holders precisely because they have a right to do withdrawals against that pool or to burn those pool tokens. I'm going to kind of leave this be. I think this is a really important research vector, and it's kind of continuing as we generalize these concepts of configuration spaces and look at what it means to combine multiple mechanisms. And I will show you this video that Marcus made that was referenced a few times. This shows real historical data using a Uniswap CAD model. And again, we can sort of see the fact that this mathematical model is not just purely theoretical or conceptual for the purpose of you know, reasoning about it. You can actually use it to look at real data, think about real data. You can use it to inform things like Kalman filters because it provides laws of motion. Definitely recommend people who are interested in the academic overlap and applicable, highly applicable, heavily used algorithms look at Kalman filters and particle filters. The sort of sign-off point here is that this opens up this research literature around path planning. Composed games are like games that are made up of many, many mechanisms with overlapping states. So for example, you use a group of liquidity pools as a price oracle for some sort of CDP provider, and suddenly there's an incentive to do a path through the graph of contracts. You might say, I'll go over here and I might do a swap or a bond, move the price on an oracle. Then I might go somewhere else and take advantage of the fact that that oracle is providing information that's informing a decision of, say, the requirements on a CDP. And then I might go back and then swap my tokens back or return the state of the previous system. And this is a bit like a path planning problem where you take 3 steps to the left, go around an obstacle, and takes 3 steps to the right. You did something and undid it in order to make it, to accomplish some other goal that wasn't possible without the other mechanism. And so, you know, a very simple introduction to path planning would be to look at Dijkstra's algorithm. This is just a Wikipedia article. And you look at the way that sort of, you know, optimal paths are found through graphs. But what I really want to point out is that most of what we're seeing in DeFi when it comes to exploits that are not really hacks, they're more like using multiple mechanisms and complex patterns, are really like the solutions to path planning problems where the utility is some profit. And due to flash loans, you can functionally finance any sequence of actions, which is a path through the network that realizes a positive financial utility. So what we're seeing with a lot of this, you know, hack, not hack, DeFi, multi-mechanism stuff is the discovery that our, you know, web of DeFi Lego blocks aren't really Lego blocks at all. They're more like connects, meaning they have kind of specific rules about what can connect to what when. And if you wire things together wrong or you plug them together in certain ways, you get unintended consequences. But a lot of the flash loans and a lot of this sort of what I'll call path planning like manipulation that goes on actually helps clean out the stuff that's unsafe or unstable. So sort of in a meta sense, these attacks are very good for this ecology of interrelated games. But from a research standpoint, we can take this from first principles and look at the way that composed games with shared states and multiple mechanisms actually result in these kinds of multi-hop, multi-mechanism, sequences of actions that you could batch up to get positive utilities. And over time, what we're going to hopefully see is that exploitive sequences sort of disappear because things break or go down or get fixed, and that the remaining sort of path planning style solutions are actually productive, meaning they're positive sum combinations of actions that make this whole web of contracts into something more like a sense-making engine and less like a sort of financial global utility optimizer, which is kind of the way that we have our markets described today, as if there's one real global utility. As we get this sort of web of interacting things that all kind of have their own local information, both at the individual level and at the sort of subsystem level or sub-game level, we can hope, and at least I hope, that we're seeing a movement towards this financial system more as a sense-making system and less as a, I hate to say it, less as an optimization algorithm in the absolute sense, more as an optimization algorithm in the estimation sense, which is kind of bringing us back to sense-making. So that is the end of my talk. I hope it was interesting.
Thank you so much, Zargham. So I have a really interesting question here, but you only have 1 minute to answer it because the Zoom meeting is actually automatically going to sign off in 5 minutes. And I do want to tell people where they can find the videos and so forth. The question is, so because you're at the intersection between academia and really also the cutting edge implementation of bonding curves and also a lot of other primitives in this space, where do you think token engineering is going to be in 1 year, in 5 years, and in 10 years from sort of an epistemic foundation perspective, but also from an impact perspective? Do you have
yeah, all right, so 1 minute, gotcha. All right, so I'll try to be as brief as possible. So 1 year. All I really want in 1 year is a cohesive community with a set of sufficiently shared values that an external party would recognize it. That from the inside perspective, we have enough alignment that we can function as collaborators to contribute to furthering this, and that externally people go, oh yeah, those are the people to talk to. Maybe the way that in a very small sense, we would think about an engineering society. In 5 years, I would like it to be functionally like an engineering society, having established some standards and norms, providing some, whether it's conferences in the traditional sense or more events like this that are ongoing learning. So if you would imagine going into that community to learn about the best practices, so it's simultaneously teaching and creating and applying standards, and that would serve as the backbone of this sort of interoperable network, because we have people who are in a way taking responsibility for the public good in the context of infrastructure, meaning not everyone should understand everything. You should trust the social institution responsible for upholding the safety of that infrastructure to continue to uphold the safety of that infrastructure. And then maybe after 10 years, we might hope that would be recognized beyond the sort of immediate field. So even at 5 years, I'm talking about largely that institution servicing other members of the crypto institution, but that by 10, maybe it's recognized even beyond the borders of its immediate sort of users. Again, the way that in an engineering society, you might say, well, look, I appreciate the civil engineers, even though all I do is just drive on roads and never think about them.
Cool. Thank you so much. That was awesome. So because we're going to sign off in 2 minutes, I would like to thank the speakers for preparing these awesome talks. I know we've been quite proactive in kind of shaping, engineering the event a little bit. So it was a bit of extra effort. I think it paid out. Also, thanks to the audience, we had, I think, maximum 82 people. After 2 hours, there was still 75 people on this call, which is a very acceptable churn, I think, for a Thursday evening token bonding curve event. Also, this was really an experiment in terms of event format. So if you have feedback on what worked well, what didn't work well, please do share it. I think Moritz, if you can share your email address, I think that would be good.
I would also like, let me just also thank the people who all joined us. I think it was quite a ride through the topic of bonding curves that we had now the last 3 hours. I hope we could meet your expectations and also demystify this design discipline a bit for you, but also give you a good impression of some real use cases along the way. So thanks a lot to all speakers for your valuable insights, but also particularly to the audience for participating. And finally, yeah, we hope to bring more such events to you. So if you want to learn more about token engineering, broaden your network a bit, we are looking for helping hands along the way. So yeah, thanks a lot from my side.